which are used for angling purpose. After the angling cycle, their meat quality is low and their processing costs are high, so therefore they are landfill. We can make use of that. We extracted lipids from there, and then we converted them using the process I mentioned. So we can directly convert the tags, or we transesterified into fatty esters, and then we convert it into monomers. So if you look at it, this is a very quick, efficient process. We use 50 degrees Celsius temperature. Within less than 30 minutes, we can convert it. One of the biggest problem is that we have to have turnover numbers more than 50,000 for process to be viable on that scale, and we were able to get those numbers by using microwaves and the low catalyst loading. Here is the example of the monomers. We had major monomers. So I'll give you a couple of examples of those. We use them to make polymers from there. For example, we separated ethylene from this mixture and used it to make polymer. So you can see here, we oxidized it, and then we copolymerized it either with carbon dioxide to make polycarbonate, because currently polycarbonates are made using phosgene gas, and that's a toxic gas. So, and the secondly, we can copolymerize with anhydride to make polyesters. And this process was quicker, easier, because we didn't try high vacuum in this case. You can see we can incorporate around 87% or so CO2. The problem is that as we go higher, the degradation temperature, it starts to degrade at lower temperatures. So around 19, 20% is good. Higher, if we are thinking of high-end application, it becomes a problem. The second example I'll give you is the diester. So we separated this diester and we made a polyester, 100% bio-based polyester. We take this diester, we reduce it to DIO, we copolymerize it, and make this polyester. The polyester is very stable, and you can see here that we can compress them easily. The problem with this is the mechanical properties are not very strong. They might be used for packaging or those kind of applications, not for high-end applications. Then we use this diester and make polyamides. So we can polymerize it with conventional amines and make high-end or stronger polymers, polyamines, for example. And you can see that thermal stability is very good. Their melting temperature is close to 200 degrees Celsius. Mechanical properties are good. So those could be a good option. We use the same diester, and we wanted to prepare some self-heatable elastomers. And we know that we have a human body, for example, skin has tendency to heal itself. It's potentially possible that polymers can heal themselves as well. So we actually started making, so take this diester, we functionalize it, convert it into acidic functionality, and then terminal alkenes, and then we can use this functionality to convert into a pre-polymer. For example, we have this kind of thiol-containing oligomer, and then using Tric, we can use this diester, functionalized diester, to make a polymer which can self-heal. If you cut it and heat it at 80 degrees Celsius for 8 hours, it will self-heal. You can cut it into pieces and compression mode it, you will get the same kind of material. The mechanical properties of this material are compared. So that's a very good process to recycle it. You can, even if it is damaged, it can be self-heal, and we can recycle it as well. We did a scale up. So we got funding to scale up and then started a spin-off company. That company is now working, had 6 employees, and they're planning to expand it further with a bigger company to produce it on larger scale. The second part, the example I will give you, is the oil sand tailing process. So basically what happens is the oil sands, the petroleum we get is extracted through 2 processes. One is that some sands have oil in there. They take the sand, they mix it with hot water, and then they separate that hot water and oil and put that hot water with all the contaminants in the tailing ponds. And we have big ponds. For example, you can see here, Alberta is one of the producers. These are huge ponds with this water, contaminated water. It's a kind of slurry, it doesn't settle down. And they want to remediate it because government has put new regulation that you need to remediate it, remove the water, consolidate it, plantation on the surface so that they can make use of it. The challenge is that this does not settle down. So we actually took this spent hand, sorry, the feathers, and we converted it into basically, if you look at the structure of this is 100% protein with some moisture. So it's a cross-linked protein. You see feathers are very strong and stiff. We What we did is we break those cross linkages, we expose the amino acids and use them for the consolidation of filling and also for the treatment of water. You can see the removal of metals. We can remove different type of metals very efficiently. And also we modified them to make more type of flocculant or adsorbents and use them for consolidation of fillings. So you can see here that we have, this is the commonly used polyacrylamide, which is a patented technology of DuPont, and they sell it very expensive. We did comparison with polyacrylamide. We can get metal consolidation. And then when we did some analysis of the consolidation, you can see that we have with polyacrylamide about 10-12% consolidation. We can get to about 35% when we use the biopolymers based on the keratin. Similarly, the water recovery is much higher. We can get water recovery around 10-12% with the polyacrylamide, but we can get to 35% when we use the keratin-based flocculant materials. When we use bigger columns, we can get the quick consolidation and optimized conditions. We can get up to 80% or more consolidation and water recovery. So this is a big project we have now. We are working with industries, and we are trying to scale it up to test in real consolidation application. This is actually real material we got from them. This is a small scale, lab scale process. So we want to expand it to larger scale. The third example I'll give you is the lignin. Lignin is one of the, you can say the second most abundant biopolymer after cellulose. And the problem with this is that it's present between cellulose and hemicellulose. And you can see here that most of the time lignin is produced as a byproduct or co-product of pulp and paper or biofuel industry. And that's mostly burnt to give energy back to the process. So the challenge is that if we convert this lignin and make really high-end materials, we can improve the revenue much more than double if we make use of this lignin material. The problem with the lignin is that when they extract or use this cellulose, they basically don't care about lignin. Lignin becomes more cross-linked, and it's called technical lignin. The problem is that we have these new cross linkages here, which are carbon-carbon linkages. It's hard to break them down. The basic units you can see here, these are 3 basic units. So if you look at these cross links and look at the stability of these cross links, the carbon-carbon linkages, you can see the bond energies are higher. These are much more stable. These are difficult to break, and therefore it's hard to make use of lignin with the conventional method. There are so many methods available for lignin volatilization. People are using different approaches. Most of the time what happens is that they try to break this alpha O4 linkage, and the rest of it is not. You can see that the carbon-carbon linkage is also there. Actually, other linkages are there. So for making use of this material, we should effectively depolymerize it. And so what we started using is we started depolymerizing it using some solvent, and then we developed a catalyst to depolymerize lignin effectively. We initially started with depolymerization, and you can see here that we tried both catalytic and non-catalytic. And so we separated the liquid product and solid residues. The solid residues, we actually purified them and used it as an adsorbent, because this could be some sort of biocarbon which we can make use of it. Most of the time people take this and discard this part. So we had those depolymerized product, we actually fractionated. We wanted to look at what we get out of it. And you can see that we were able to separate them into different fractions. And you can see that when we used a temperature of 140 degrees Celsius under 30 minutes time, this is a more of optimized conditions. And we were able to get low molecular mass components. And therefore, we actually looked at all those fractions which we got after fractionation. You can see the PDI decreases, the hydroxyl functionality also changes, and you can see it's comparable compared to lignin in some cases, original lignin. Hydroxyl functionality is useful when we are making use of it for different applications, especially for when we are talking about making polyurethanes, for example. So we characterized it to look at different type of hydroxyls. We can see that we have got different hydroxyls. We have more, um, if you look at the condensed or non-condensed or carboxylic hydroxyls compared to the craft lignin, which is the black here, you can see we can get really carboxyl low, and also some of the condensed and non-condensed also lower fractions. So that's, we are basically breaking down not only the alpha linkages, but also the carbon-carbon linkages. So here's, these are some of the fractions we separated after fractionation. We use these fractions to make polyurethane, because polyurethane is one of the polymer which has a huge market. We use it for a variety of different applications. So what we did is we took this lignin-based bio-oil and mixed it with some of the other bio-oil, which is commonly the polyol, which is commonly used for lignin polysis. And we wanted to increase or substitute with this lignin-based bio-oil and made different type of polyurethanes. You can see here. If you look at the mechanical properties, so this is the original polyurethane, which is synthesized using commercial polyol. We replaced it or substituted with the bio-oil produced from lignin, and you can see the color obviously is going darker. However, images, as we go higher, as you can expect that the bio-oil try to more of it accumulate or crystallize, and therefore the mechanical properties or other properties become weaker. We can go up to 50% or so, and then after, as you go higher, it becomes agglomeration problem. The catalyst we synthesized to improve the conversion was the graphene oxide, and the reduced graphene oxide, we sported nickel on it. And you can see when we converted this catalyst, we used two different sports, phos and graphene oxide. And one of the sport was acting as a catalyst to degrade. You can see that degradation temperature. This is the original DPOS, for example, if you look at this one here. And as you add nickel to it, it degrades quickly. So that's because it's acting as a catalyst itself for degradation. So it's not good for that process. We use then these catalysts, especially the other phosphorted and graphene oxide sported. You can see we can get up to 90% conversion with yield 60% or so. And then we looked at different components. You can see we can get up to around 70% or more bio-oil, which is really a good conversion with lower molecular mass when we use this reduced graphene oxide-based material. And this is some of the major products we got. So you can see we have vanillin, which is a big, it's very important monomer which people are looking at to produce from lignin. Similarly, we can produce catechol, higher percentage of catechol, and other products which have a huge market value. So that's about lignin. And then the biocarbon we have left, we use it for adsorption of metals. And we can see that we were able to absorb different metals. We targeted these three metals because these are one of the problems in the oil sand tailings. And you can see they work even at basic acidic pH, which is a problem. The absorption capacities for these are really good. And in summary, I would like to convey a message that we can use waste and make materials out of it. We can make monomers and biopolymers for consolidation of tailings or water treatment. Lignin, this could be a new petroleum because it's a huge volume. This is the second largest biopolymer or not. It's underutilized. We can make use of it. And I just wanted to let you know that I'm organizing this 19th International Society of Biocatalysis and Agricultural Biocatalysis conference in Banff. It's one of the beautiful cities in Alberta. This is a resort town in Alberta. And we are still looking at whether we will be organizing in any of these places. Lake Louise is one of the very famous lake in Banff. And Banff or Jasper also has a lot of wildlife, and it's really a beautiful place to visit if you want to. I would like to acknowledge my group members, especially my collaborators, Dr. Chen, Joshi, Qureshi, Siddiq, and Evanchi, and the people who have done the work. So these are the ones who have done the work. Obviously, I don't work in that. I'd like to acknowledge the funding agencies as well, and thank you very much for your attention.
Thank you very much, Dr. Amanda. That was an excellent talk, especially I would say with reference to Pakistan, because we have a lot of waste material. And I always wish that waste material should be converted into some value-added product. So I think this is a guideline for researchers doing work in our country, that they should learn how we can convert, as Dr. Manula is working on lignin, on animal feeders, and so many things. So I invite any questions to Dr. Manula, please. Any questions from all? Yes, please.
That's a very good question. So the bio-based plastics, they have two different types. One is that they are degradable, another one which is non-degradable. Even the degradable, they further have two different types. Some are compostable and some are generally genuinely degradable. So compostable means you have to have certain conditions for them to degrade. Otherwise, if you throw in the environment, they can generate microplastics, and same problem what we had. In water or they are compostable. So to your question, the biopolymers we synthesize, not all of them are biodegradable, and some of them are biodegradable, but those, then again, we need to figure out that they are, so the biopolymers that previously presented, they are biodegradable, they can degrade in soil. The polyurethane, we didn't test it yet for biodegradability. We are hoping that this will, but we don't know yet. Thank you.
Any other question, please?
Sir, I have a question.
Yeah.
Sir, are these materials being used on commercial scale? If so, how much recovery needs a yield?
Yeah, so they're not being used on commercial scale at this time, except the one example which I gave you, the spin-up company we started. So that company is still, when we start the company, it takes time for them to really produce and go to commercial. We call it public. Takes 10 years or so. So they're producing it, but they're producing on smaller scale, where they give to different companies for testing, those who are users actually. And then once they get more funding and they go to bigger scale, we call it commercial scale. And then product becomes available in the market. So none of them is available in the market at this point. The second, the feather-based consolidation, tailing consolidation materials, we're testing them with industry, and the target is to commercialize them in next 3 to 5 years. Especially when we have the tailing industry, which is producing tailing, and they're really looking for something. So hopefully we'll have something available for them in next 3 to 5 years.
Are these materials are viable commercially on the basis of cost?
Yes, so that's very good question. The cost, as I mentioned before, these are third generation biomass, these are waste materials. And so the cost is, when we spoke with the poultry process industry, they told us that we will pay you for, we like to deliver you free. So we generally they pay it for dumping or disposing. So that at this point it's very cheap and therefore are commercially viable. When it goes to larger scale utilization, maybe there will be some cost which industry will look for those who are producing feathers. But that will be very low compared to other materials. For example, if we start asking for protein, which we are using, is highly expensive and so we cannot use it.
Very much, sir.
Thank you very much. Thank you very much, Dr. Manla. Our next speaker is Dr. Puram Joya. He is Associate Professor in Chemical Science, Islamic University of Medina, Saudi Arabia. And the title of his talk would be Innovation in Chemical Science for Energy, Environment, and Economy. Dr. Joya was Assistant Professor at King Fahd University, Saudi Arabia, and a faculty at UET Lahore. Dr. Joya has more than 80 high impact factor research publications, more than 30 QI journal publications, and with a high index of 30 and over 450 plus impact factor. There is a long list of his credentials. Cutting short, his research accomplishments include 2 faculty research awards and so many other credentials on his name. So I invite Dr. Joya, please to come and give his talk.
Bismillahirrahmanirrahim. Thank you very much, Session Chair, for the kind introduction. And yeah, just a few moments. Okay. Actually, it is more or less the same title. I intentionally did not change it. With respect to umbrella of my research, it is actually the let's say developing or understanding the natural processes and trying to convert them, let's say chemically, technologically, or physically into the lab. So the devices I'm working on actually they are trying to mimicking or biomimicking the process of natural photosynthesis. Or let's say we are trying to make a leaf which is a biomimic of a natural leaf, and we try to mimic those processes also going on into the leaf. So we call those devices, those systems as artificial leaves. So they are actually, let's say in artificial leaf, the process will be artificial photosynthesis. Just like a natural photosynthesis, in artificial photosynthesis or artificial leaf, the primary, let's say the first part or first phenomena is the light capturing, light harvesting. Then we are doing the water splitting and CO2 reduction, or in some cases, directly conversion of water into, or let's say water splitting into hydrogen. So this is like in a nutshell, but I will show later on a few of the other research instances we have, like we are also recently started working on CO2 carbon dioxide reduction also using these artificial leaf devices and also biomass conversion. Okay, so now actually the focus of this research, just like plant leaves, we try to utilize the abundant resources we have on this planet. Like, the previous doctor was saying, the biomass is, we have almost everywhere in the world, and it's a waste, sort of waste or a byproduct of so many things. And it is a very good idea to utilize this. The same way we are trying to focus on Earth's abundant resources. So one of the big resources is sunlight. And again, like plant leaves, sunlight is like a driving force, driving energy for those at least two chemical processes going on in the plant leaves. So our focus is same on the plant leaf. Then for the let's say starting material, primarily we are working on water. So you will utilize water and develop the system which can utilize or which run with the sunlight to split water into hydrogen. And then, of course, like I said before, we started to focus also on biomass. So biomass conversion into different bio-based plastic, and also few examples we just started recently to convert biomass into fuels or fuel chemical also. Then CO2, in fact, CO2 is not abundant resource or commodity chemical. But the air in which we are breathing now, roughly CO2 is around 410 ppm, which is a very, very small amount to utilize it on a bigger scale. But when we consider CO2, which is coming, let's say, directly within the vicinity of the powerhouses like we have in Pakistan, and because I now come from Saudi Arabia, and all of the electricity is coming from the burning of those fossil fuels. And within the vicinity, the amount of CO2 is much, much greater than the CO2 in normally in which we are breathing now. So in that sense, of course, we can also consider CO2 as a commodity chemical. And then, like playing few magic, few tricks in the lab, we try to convert them again primarily to hydrogen, which can be utilized as a synthetic fuel. But of course, we can convert CO2 also into carbon base. We call it carbon neutral because if you utilize CO2 to make fuel, the amount of the carbon will remain the same in the atmosphere. So you are not adding more CO2 into the environment. So you take it, you combust it, and you put it back. I mean, it's not a really safe way, but still we can term it as a carbon neutral fuel. But of course, compared with this one, hydrogen is a clean carbon fuel. So there is no carbon footprint whatsoever in the hydrogen. So, and also, like I said, the biomass, we are trying to convert biomass into bioplastic, a little bit different compared to what doctor was saying previously. And of course, fuel distances in this biomass can also be converted into biofuel, but not the ethanol-based or alcohol-based biofuel. Very quickly, with respect to research application, we are working primarily again on water splitting and CO2. We also do light harvesting, electroorganic synthesis, more or less using the same devices which is utilized to do water splitting and CO2 reduction. And then electrochemical sensing and biomass conversion also more or less based on the same device principles. And then we have some side projects going on. Actually, they are like helping or aided techniques we use in our research, but of course, in some cases, they may become independent research projects. And how we do that? I'm skipping it because I'm sure many people know about hydrogen already as a fuel, but very, very briefly, I mean, there are many ways, of course, to compare hydrogen as a fuel with carbon-based fuel. But one of the biggest attraction is, of course, if you combust hydrogen in the fuel cell or any other way, of course, the product is only water and nothing else. Plus, compared to, I mean, it's like intrinsic energy value a fuel may store inside it. We call it energy density or energy content in terms of megajoules per kg. You can see from this chart, the hydrogen is almost 2.6, 2.7 times higher in terms of having intrinsic energy capacity of storage compared to the gasoline base or the fossil based gasoline and diesel which we are using today. Plus, of course, another big use of hydrogen as a fuel. I mean, you can, of course, use it as a combustion fuel directly in the internal combustion engine, or the best way is to utilize in the fuel cell to give you energy or electricity. In internal combustion engine, the maximum efficiency of a carburet engine is 25%. I mean, you cannot get more than that. And the minimum efficiency of a fuel cell based, let's say, vehicle system is 75%. So this is a beautiful way of utilizing hydrogen. The process is known as cold combustion because this is an electrochemical combustion, and instead of generating heat, we generate electron, and then electron are used to drive the automobiles. So this is the concept. But of course, if we talk about in Pakistan, we have other two very huge uses of hydrogen. We use hydrogen to make ammonia, and then ammonia is used to make urea fertilizer, and we make in huge amount in Pakistan. And plus, of course, the banaspati ghee we almost eat every day. The hydrogen is used to saturate the oil to convert it into banaspati ghee. Nickel nanoparticle thickness is used for that process. This is again a very briefly what plant leaves are doing actually. They have chlorophylls. Chlorophyll capture the light. Then you have the charge transfer. Then on the one side, which we call P680, which is reaction center, what splitting is going on. And then on the other side, which is P700, the CO2 reduction is going on. In some lower plants, like many algae, they do have the ability to directly convert those protons into hydrogen rather than CO2 fixation. And one of them is Chlamydomonas renhardi, and I think other one is Nostoc, as long as I remember them. I will skip this part. This is like a little bit phenomena, but I already explained briefly that they do the energy harvesting. Actually, plant leaves are not working exactly like the material solar cell, silicon solar cell we use. They use this chlorophyll assembly, which is chlorosomes, in fact. And chromosomes just absorb the energy and funnel it or focus it to a region which is known as the direction center. For the anodic part, this is P680. So chlorophyll absorb the sunlight and then focus it to P680. Now P680 is doing the charge transfer. It is not the chlorophyll. In our silicon solar cell, it is absorbing the sunlight and also doing the charge transfer on the same place. That's why we don't have so much efficiency compared to the natural leaves or plant leaf. Then, of course, we have the electron transport and mass transport chain in which electron or the holes are separated by a series of channels. And then electrons are transferred, or taxi we call it, to the CO2 reduction center, which is known as P700. And then there is a separate mechanism for the proton transport. And of course, CO2 from the stomata directly reach here, and then we have the efficient, let's say, CO2 reduction. There are a few other things. I mean, if you go a little bit detail into the P680, there is a manganese calcium oxide nanoparticle actually, which is acting as a catalyst for water splitting. So plant leaves, half of the assembly is organic or organometallic, you can call it, and some assembly is nanomaterial. So it's a mixture of organic, inorganic, and physical chemistry. Everything is going on at one. Let's say in the leaf at the same time. So we, like I said in the very beginning, we try to understand. Of course, we cannot replicate the leaf in the artificial world, but we try to understand phenomena. We try to replicate in a material world or chemical world, let's say, and we try to, let's say, manifest the devices if we able to do water splitting or this whole phenomena as efficient as fast leaf traveling. I will skip this part. There's a little bit details. In like I said, in lower plants, in some lower plants, there are actually existing these three natural hydrogenase enzymes. So iron, nickel, iron, and only iron. They are bio-based, totally bio-based, and they are responsible for the direct proton reduction instead of CO2 fixation. So those lower plants actually are directly doing hydrogen. But of course, hydrogen they are releasing is not so huge amount. I mean, we can commercially, we can apply those bioorganisms and make huge amount of hydrogen and then commercialize it. But this just like example, we can learn the message we can learn from these natural enzymes, let's say. So our way of, let's say, representing an artificial leaf, like I said, we cannot copy paste exactly the natural leaf, but we try to understand the phenomena and, let's say, present it in our way. So our concept of artificial leaf is we need to have a separate electrode for anodic reaction and cathodic reaction. And then, of course, you can have a very, let's say, thin membrane or partition, which allow only the mass transport and not the electron transport. So it is not, it's not like a short circuit connection. The two electrodes are sitting right on each other with a small thin membrane, which is in fact insulator, but it allows the efficient.
Dr. Nasir Mahmood, next turn is yours to present your presentation.
With respect to the visible region of the sunlight. And then, of course, you can have it. And in some cases, of course, you may apply donor-acceptor couple because you want the lifetime of those whole electron you are generating. You are talking about nanosecond or picosecond, and it's a very short lifetime of electrons. So you need to either utilize electron in that time span, or you need to take electron or hole away from each other. So one way, of course, many of those catalysts are not that fast, which we develop in the lab. So one way to separate maximum amount of those charges is to apply donor acceptor couple. So they take proton and electron away from each other
for some time. And then your catalyst will have a little bit more time to work on it. Like I said, the catalysts we normally develop in the lab, they are not as rapid compared to the natural catalyst. And then, of course, based on this, let's say, design, we can have hot splitting, but now, of course, many oxidation processes we are going on. We can do electroorganic synthesis. We can also do biomass oxidation here. And then, of course, you have the proton release. Either you are using the biomass or the water, and then electron transfer going on the cathodic side. Same way on the cathodic side, you have the light harvester, charge separator, and then the catalyst. Now here we have bigger, let's say, choice or selection of the catalyst. Primarily, we can directly go for the proton reduction to make hydrogen, or zero reduction, or like other phenomena or other processes you can also do once you have this device ready and range of the catalyst for different applications. Okay, so first part of developing an artificial leaf is developing an artificial antenna system for the light harvesting system. You know, in the plant leaf, I might said before, they are using this chlorophyll molecule with magnesium. The chlorophyll molecule have a magnesium center inside. You know, let's talk, I mean, chlorophyll molecule is not a very good when we talk about an artificial device. If you try to take out the chlorophyll molecule and put it in your hand in the air, it is highly sensitive to this white light, the moisture, and CO2. I mean, it will destroy itself less than a second. So, I mean, it's impossible to take it out and then put it in the device. So what we did, we tried to, let's say, make a very similar molecule, which is stable in white light, in moisture, and in oxygen. Plus, other thing is, you know, in fact, chlorophyll molecules are not just sitting in the leaf and absorbing the light. They have a special aggregate, we call it. Actually, it's a three-dimensional aggregate, which is known as chlorosome. The difference between chlorosomes and chlorophyll is chlorophyll molecule normally absorb around 645 nanometer. And the chromosomes absorb around, I mean, the lambda max is around 740 nanometer. So this is the beauty of chromosomes, that once chlorophyll convert them physically, let's say, into chromosomes, the range for the absorption of light increases from 645 to 740 nanometer. So what we did is, of course, first we developed this synthetic chlorophyll module. So more or less, we try to prepare same chlorophyll molecules, but instead of putting magnesium, we put zinc. Now, this artificial, let's say, biomimic, I would call it, zinc chlorophyll are stable to white light, moisture, and oxygen. Still, when I was making these devices, I try to use green light to make sure that we are not destroying. But of course, we have done more, many photophysical experiments to make sure that these synthetic modules are stable compared to the natural module of the chlorophyll molecule. Then to make the chlorosome, I mean, it's difficult. You ask the molecule to obey you, but of course, you can tune your system in a way that molecule has to obey what you want from the molecule. So we give this, we provide this nano, let's say, template for the molecule. So they have to go, I mean, once they go inside, we change the polarity, and then those molecules have to organize themselves in a tubular manner. So we call them a synthetic or artificial module of the chlorosomes. And then, of course, we did some, like I said, some photophysical experiments to make sure that we had converted those synthetic chlorophyll modules into synthetic or artificial chlorosomes modules. And you can see still more than 85 to 90% of the transparency of these devices remain stable. And then, of course, the next step is just to put anodic on one side. You have to put the donor acceptor and the oxidation catalyst, and on the other side, it is just a small disc of 1.5 centimeter diameter. So you can imagine it's like size of your nail, and this thickness is around 20 micron. And so on the both sides, you can have the catalyst, and then you just have to put this one in a cup of water, glass of water, put a little bit like a pinch of NaCl, and put it in the outside in the sunlight. And you will see in few seconds the oxygen and the hydrogen bubbles coming on both sides of the device. This is like a standalone device. Of course, the efficiency is less than 1%. Okay, because of the time constraint, I have to quickly forward. These are few examples of participating catalysts we developed from let's say starting almost 10 years ago. We developed this first module, which is the organic organometallic, but then most of our research, like last 4 or 5 years, is on inorganic materials. So we do develop many inorganic materials using different techniques. We use electrodeposition technique, anodization, quantum spray pyrolysis, solid state tensor, molecular precursor route, and then of course few little bit advanced techniques like CVD, PVD, and of course, in some instances, laser-based deposition and even atomic layer deposition. It's just to let's say to devise you have designed your system, and then you try to mimic, try to make something because you have some concept and try to make different different thickness, different sizes of those thin films nanomaterials to have this catalysis or electrocatalysis going on. I will skip there are few examples. I mean, you can just go through the literature. There is no time to go into the details. Yeah, for the quickly karo with this device, quickly go forward. This is an example of anodization of the copper. Aage. Okay, keep on going. Spray pyrolysis, few examples of spray pyrolysis quickly, yeah. Examples of colloidal thin we develop. It's a very simple method. You can develop it in your kitchen. There is no hard chemistry or chemical going on. This is a collaborative work with lumps with Dr. Irshad. I think he or he will be around here sooner. Then we have this CVD based films in palladium and of course cobalt and nickel. We also developed using PVD. Then CVD. I just want to show you example of biomass conversion. चलते जाओ आगे. Yes, keep on going. This is few examples of CO2 reduction we are doing still. Actually, one of my PhD students here, she's working in UET. She will be presenting a little bit more details of this CO2 reduction in the poster. Again, next. Okay, another biomass. Yeah, okay, we actually, the purpose of this project when I started in the Denmark Technical University was to develop a replica of this PET plastic, which is PEF. So actually, we want to replace the terephthalic acid in this plastic with the new biogas plastic. And we want to have all those ingredients coming using the furan dicarboxylic acid and ethylene glycol coming from the biomass. So we focus primarily on two starting materials from the biomass. First was the, let's say, furfural-based molecules. Actually, this HMF, which is hydroxymethyl furfural, you can directly get it from the biomass. And next is the glucose, or of course, glucose and then sugar alcohols coming from those. You can also directly get it. In our case, we use xylitol and sorbitol. So this chemical, we can oxidize it selectively, let's say, electrochemically, or using our device to make it, to convert it into furan dicarboxylic acid, which is the replica of the PET, let's say one ingredient of the PET which is present in this plastic. And then of course the ethylene glycol can also come from the biomass. So you can have this oh yeah, आगे बढ़ जा रहा है. Oh, बहुत आगे चला गया. Okay. So this ethylene glycol can be achieved from xylitol or sorbitol, electrochemical reduction. And then of course HMF can be converted into dicarboxylic furan. And then you can of course condense them together by polymerization reaction to make this new plastic, which is PET. So PET is compared to the PET. PET is non-natural, non-biodegradable, and almost non-recyclable. I mean, conversion is not, I don't call it recyclable if you convert this plastic into let's say fabric or candy chapel, something like that. But of course, some people still call it recycling. But compared to this PET, the PET is 100% natural because it's coming from the biomass, almost 100% biodegradable. And of course, it's 100% recyclable. You can convert PET easily back into PET, or even in some cases, you can convert this one, the PET, not the PET, into its starting material, which is FDCA and ethylene glycol. I will just try to, we started this project like we of course, one of my students who finished her PhD, we have of course a few examples also in the literature now that we have developed different catalysts which are which are efficiently converting, but the main emphasis is on selectivity rather than efficiency. So selectively converting HMF into FDCA with more than 90% yield in one direction. I think I will finish it there. Let me see what various points that I have. These are few examples. They are already in the literature. You can see them. I'll be just going to finish it now. We are also working on few, let's say, commercial projects. Somehow they are directly or indirectly linking with our research. One of the projects which we are doing with the Tric in Pakistan is to developing these catalytic converter to reduce the emission of the internal combustion. Then with one project we are working on the She concept car, which is solar, hydrogen, electric, and gasoline. It has actually 4 modules. This project is very slow, but I hope, because I'm in Pakistan now, I hope with the collaboration of one industry, I cannot name it now because they actually stopped me to name now. So we are already collaborating with one of the HEV, which is assembled in Pakistan to let's say to conduct this project or carry on this project. And one of my own project is working is on developing this electrochromic coating for the windows and for the glasses for the eyelid, also for the windscreen of the cars, even the side.
What's happened?
glass. Keep that one. Yeah, thank you very much.
Thank you very much, sir. Any questions?
मुझे बता दो हमसे कब
Sorry, just wait. Where are you? Okay. Did you Google before asking me this? Did you Google? अपना homework नहीं किया हुआ आपने? You know, in I will tell you, in Sweden, because I was part of that consortium back like more than 10 years back. There's a consortium named Swedish Center for Artificial Photosynthesis. Now they have in Germany, in USA, they have the biggest one in Caltech now, the JCAP, Joint Center for Artificial Photosynthesis. They are all working on this. Of course, they are much ahead than me. I'm working alone, a few people, but they are on a bigger. If you talk about the commercial application in Sweden, they already have the fuel cell buses going on. I think 4 or 5 years back, I saw a first fuel cell vehicle even in DH in Pakistan, Lahore. In Japan, they have now fuel cell based train which is running on. And I'm sure if you Google it, you will find much more than what I'm telling you. So of course, that's why it's a highly demanding, high risk project which is going on in many, many parts of the world. Of course, there are huge implication, huge application with respect to commercial and let's say even on a domestic scale, small scale also.
The stability of these synthetic material go in hand with that of nature molecules.
You know, actually, I told you we are working on inorganic and molecular materials more. I mean, both. Of course, with respect to molecular material, under these high oxidation potentials, stability, of course, is a big problem. But you know, nature is doing, like I said, nature is not using one molecule to do all the purposes. Nature is using 4 or 5 different, let's say, composition of inorganic materials to stabilize it. Even in nature, the entire photosynthetic assembly is sort of, let's say, reassembling itself in 30 minutes. So every 30 minutes, one photosynthetic process, I mean, one cycle is going on inside that 30-minute cycle. 2 hydrogen molecules are being manufactured every 1 millisecond. So you can count how many hydrogen molecules are being synthesized per
Bruno, next turn is your. Can you please share your slides? Bruno, can you please share your slides? Bruno, share your slides.
They know more the bachelor degree in chemistry, degree and PhD in organic chemistry.
Can you hear me?
Just start your presentation.
Okay, can I have a confirmation if you are receiving me?
Yes, we can hear you. Just start your presentation. You have a short period of time.
Okay, so, good morning. My name is Breno Esposito. I am from University of São Paulo in Brazil. And I would like to introduce my talk by first thanking the organizers of TRIC 2024 for the invitation. And the topic of my talk today will be how to connect bioinorganic chemistry for either clinical purposes to environmental applications. So the title of my talk is The Iron Road from Hematology to Chlorophysiology, where I am going to discuss the bioinorganic aspects of metal, the delivery of metals to organisms in water, and how the same kind of compounds can be used to treat metal overload diseases. So my lab has been traditionally dedicated to bioinorganic chemistry in the specific sense of the essential trace elements, which are these. Today, I'm going to talk a little bit about iron, more specifically, and a little bit about manganese as well, because bioinorganic chemistry of iron has been a very long interest for me. The chemical principles that I will be using to discuss everything I have in this talk are the concepts of complexation and chelation. So these metal compounds, they can form structures like with organic donors, like metals, like organic molecules in biological systems, which are called complexes. So some of these complexes, these molecules can interact with the d orbitals of these metal ions from the d block of the periodic table, and form structures that we collectively call complexes. Some of these complexes, they have like a lot of different points of interaction with metal ions, such as, for example, enterobactin. And this specific complexing agents are called chelators because they form these structures that look like crab spins in the metal from several sides at once. So the important point for me here is that complexes are very stable. The chelators form very stable complexes that can render the metal very, very, very soluble in the biological medium. Like, for example, iron enterobactin forms a very strong complexes of log of stability constant ranging for 40 to 49. So these are very, very stable compounds, and they alter very much the reactivity of these metal ions. And specifically, they will alter the bioavailability of these metals. So we can use chelators, we can use these organic molecules, both as a means to remove metals from intoxicated organisms, so metal overloaded organisms, and to deliver metals to metal depleted organisms. Just a second. Okay. Like iron, for example, in the mineral form, it's poorly absorbable by organisms, but when it's present in chelated forms with organic, either biological or synthetic organic molecules, this iron is made much more bioavailable for organisms. The beginning of my career, I was concerned about iron overload disease. So the idea was to use metal chelators, these organic molecules, to remove metal, the excess of iron, from within the human body. Like iron overload disease can be either primary or secondary, like they can be either genetic or acquired by multiple transfusions. And in the end, they will cause the same problems, which is a very heavy burden of iron that can be toxic for the patient. So iron overload can be treated by either by phlebotomy, like you remove blood from the patient, or by chelation therapy, which is the chemical approach most successful. These are the three chelators that are used for the treatment of iron overload, but all of them have either major discomfort and high cost associated with the treatment, or very serious side effects. So as I was saying, in the beginning of my career, I was looking for new chelators to try to overcome some of the side effects of these iron chelators from the treatment of this disease, which led us to develop this environmental bioinorganic chemistry and metal drugs lab in my university, where we have this three-pronged research. We look for new chelators to try to do new tricks on iron chelation. We try to use chelators to remove the toxicity of metal compounds like lead, which are very toxic, and there's no much surprise for that. And we can use chelators to introduce toxic metals to organisms, because some of these chelators are very, they have specific absorption pathways to cells and organs, so you can load these ligands, these chelators, with toxic metals, and then try to use this Trojan horse strategy to load toxic metals to organisms. So I'm going to go very quickly about this first part, because this is not really what I'm doing right now. The first part of these projects have been the search, the synthesis or the repurpose of chelators. So we either produce the new chelators or repurpose the old molecules for new tricks for the treatment of iron overload disease. So we either took molecules that are like phytochelators or organic molecules, natural organic molecules that can be used for binding iron, and try to see if they had any therapeutic chance of success. These are some examples, including like an anti-inflammatory drug, which has a nice, beautiful possibility of interacting with metals here. And we produced our new chelators. We took siderophore as a basic structure, this trioxamine, which is a natural molecule, and we try to derivatize this trioxamine to make it either permeable to the blood-brain barrier or permeable to mitochondria. So we just modify the terminus, the amino terminal part of this molecule with carrying ligands to try to direct its location in the organism, and making even some multi-platform diagnostical tools, like binding this ligand molecule to proteins and loading with different metal ions, so you can have different uses for the same basic chelator. So this is all good and well, but we are like looking for new possibilities of new chelators. So 10 years ago, we started looking for new chelators in the sea, because seawater is terrible for iron solubility, because seawater has the wrong amount of oxygen, the wrong pH, and the wrong salinity to keep iron soluble. So, and nevertheless, iron is bioavailable for organisms in water. So what's the trick? Who are the molecules who can make iron soluble and bioavailable in this very hostile environment? that was an idea we have to try to look for this new, potentially new drugs for the treatment of iron overloaded diseases. So start to go to the sea for this. Our first project, this work was doing in a facility of our university at the Brazilian coast, where we collected marine sponges and try to extract different compounds. I'm not going to through all the details right now because it's a little bit exhaustive to go through it. But these are all the species of sponges we looked into. So we found some of them were very good iron chelators. We have a very high throughput, very convenient way to assess iron chelation of any natural molecule with very low amounts, very low concentrations, and it's a fluorimetric microplate based assay, very easily to deploy. Some of these extracts have a very good antioxidant activity, so they can really kill.
Can you hear me? Sorry, I'm interrupting you, sir. We are running short of times. Can you please wind up in 5 minutes?
Yes, I'm going to finish. So, and then we try to look for iron chelation, metal chelation, to try to load metals to organisms. So we try to do the opposite. Instead of looking for molecules to remove metals from the organisms, we try to put metals in the organism by means of some specific chelators. And this was done specifically targeting corals, because corals are under stress, thermal stress right now because of anthropogenic activity. So we try to use these chelators to deliver metals to corals. These are some of these early studies we did a few years ago, where we found that some of these chelators, they are better. Some chelators are better than others to do this kind of loading to corals. And the order of addition is the important. The chemical speciation of the chelator and the order of addition to the chelator is important, and can even preserve the coral against heat shock. And then we use the same strategy to load manganese, which is a very important mineral for photosynthesis in the corals. And some of the either manganese salt or manganese with few ligands can increase the reactivity of these photosynthetic centers of corals. We recently developed a collaboration to make some controlled devices for corals in seawater, and we did find some good results. Specifically, we can increase oxygen production of the photosynthesis under thermal stress without increasing the amount of algae that are symbionts to the corals. So, I mean, the manganese can be deployed in the corals very easily through this strategy. So, manganese is good for corals. Iron is not so much, but manganese is much better. And they have very fast acting, these devices. They can have very fast loads after 1 hour, 1 day, we can find some very positive results. And with this devices that can be put and removed from the coral reef whenever needed. So I'm going to wrap my presentation. Thank you all the collaborations I have had from the last 2 years. And I'd like to thank specifically 2 Pakistani students that went to my lab for sandwich PhD programs, Dr. Amir Hashid, who's nowadays a professor in the University of Kotli. I'm sorry, I probably am pronouncing this wrong. And Dr. Faiz Ahmed, who is at the Government College and the University of Faisalabad. And thank you for your attention.
Thank you very much for your presentations, for your time. If anyone have any questions, then write in the comment sections. Okay.
Dr. Nasir Mahmood, please share your screen.
Oh, sorry. I don't know if anybody's trying to ask something, but I don't have the chat and I cannot hear you.
Dr. Bruno, you can unmute your mic. Thank you very much. Sir, you are on air now. You can proceed now, sir.
Can you see my presentation?
So yes, we can see your presentation. So we are watching your presentation. Can you please start your presentation?
Sure. Thank you so much. Assalamu alaikum. And I will be talking about the importance of water and role of catalyst for a low cost hydrogen production from water through electrolysis. Before going to that one, I will just highlight what we are and what we do at RMIT. So we are basically a materials for clean energy and environment research group. My group mainly focus on developing different kind of materials through different approaches. So that can be a physical, like a liquid metal based synthesis, wet chemistry, and the physical approaches that traditionally we apply. But we choose the different kind of techniques depending on what kind of materials we want to produce, their properties. Either they need to be like a 2D, and even in the 2D, like how much thickness and those kind of things we can easily control. We can go from a large centimeter area single crystal sheets, half a nanometer to one micrometer size, and then we can also design the other kind of heterostructures. So and then we apply them into different application. One of them is like energy storage and conversion, where we apply them for the batteries, supercapacitors, hydrogen production, and different kind of catalytic reactions. We do have an interest into biomedical applications like in vitro and in vivo early disease detection, drug delivery,
Sir,
and
just a minute, sir. Sir, we can't see your slides moving. It's just stuck on the first slide.
uh,
Okay, thank you.
yes,
Thank you very much.
sorry.
Sir, you stop your screen sharing.
Just give me a minute. Can you see my screen now?
Yes, we can see your screen now.
And slides are moving?
Yes, 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 we can. You can proceed now. Okay.
Okay, thank you. So I was talking about uh, like we apply these materials into different applications, ranging from energy storage to wastewater treatment and microwave absorptions. Mainly, we why we are motivated into the energy and environmental applications. If you look at these two pictures, these are the two major cities of the world. One is Beijing, and other one is London. I think nowadays might be the Lahore has the same issue, same situation, that where we have a lot of pollution around us, and this all is caused by ourselves. We use our resources, we use them very brutally and very badly, that we cause all those kind of things. Now it's our duty to see what we can do. Is the one option that we can live like this. We put mask on our mouth and try to breathe, but we experience from the COVID that it will be very difficult for us. We can't survive. Might be humans can do it, but animals and the other living things on the planet, they can't do it. They are not used to these kind of things. So it means this is not the way that we can survive on this planet. We need to think what we can do. So what we think that it's the only possibility, we stop using those kind of polluting energy sources. We should move towards the green and clean energy systems. Among the green energy, Hydrogen emerges as the one of the greenest and the cleaner energy because the byproduct of hydrogen use is only water. That is not causing any kind of problem. But the production of a hydrogen is still a problem. Like mainly 96% is directly or indirectly is produced from the fossil fuels or a fossil fuel based sources. That is not the wise to produce it. It's the only way if we want to have a clean environment and green energy sources. It should be 100% carbon emission free. So that is only water splitting. That is at a very early stage. Still in water splitting, we are utilizing non-renewable energy sources. So that's the one challenge that we need to overcome. But water splitting has its own many challenges, especially high energy consumptions. When it has a high energy consumption, producing hydrogen through water splitting is not affordable. And so for that, what we are doing, we are developing different kind of a catalyst. And being a chemist, we know that what catalyst does, they just only speed up the reaction and lower the energy and efforts to do that reaction. And in water splitting, there's a two different kind of reactions occurs at anode and cathode. At one side we produce the hydrogen, another side we produce the oxygen, and both of these reactions has their own demand. They have their own challenges. Some of these reactions preferred in alkaline conditions, some are preferred in acidic conditions, and the catalyst can't work into two different situations, and we can't produce electrolyzers, which are the two different kind of electrolytes or the water sources over there. So what we need to think, either we improve the one of the reaction into the similar condition where the other is happening, or we have the bifunctional catalyst. So that's what we are doing at the moment. But before we move towards that one, we also need to consider that we need to split the water into hydrogen and oxygen. It means water plays very critical role here. So water define the current outputs, water define the efficiency of the system, water define the durability of the system, and water define itself what kind of a system you can utilize. So we have a different kind of a water supplies. One is a fresh water. We deionize it and use it. That's a very easy to use. But we know that in the world water supply, the fresh water is only 3%. Among that 3%, we only have a 1.5% excess for the drinking and daily life expense for the life and to survive on this planet. If we use that one, we will be shortage of water. We already facing a critical shortage of water supplies, and to meet the hydrogen requirement in the world, we need a water supply of equivalent to a one developed country of 62 million people. It's for a developed country, so it means it has a very huge consumption of water to meet the hydrogen demand in the future. So there is a no way that we can utilize the fresh water to produce hydrogen. The other two sources that are a plenty of sources around us, one is seawater, that is an infinite source to produce the hydrogen. Another, we produce millions of tons of wastewater every year, which we treat and untreat and pollute our freshwater systems. We can also utilize that one. If we start using wastewater and seawater, the advantages are it has a very easy social acceptance to produce the hydrogen. It can reduce the cost of the hydrogen production, but they are very hard to utilize. We know that wastewater and seawater both are highly contaminated. They have a large number of different kinds of ions which kill the catalyst, which kill the electrolyzer. We can't utilize them. So today I will specifically talk about the seawater use. So why we think the seawater is the best choice? Because we have a different kind of energy sources at the coastal. So we have a water over there, we have wind energy over there, we have a tidal energy, we have solar energy. If we have our electrons and molecules both at one place, why we need to transport them and then go somewhere and do the reaction we can do at there? We have both of them in a plenty, so we can produce green hydrogen. And secondly, but the problem comes here, the seawater, it's very hard to utilize the seawater. And if you look at the energy distribution around the coastal zones, the red area, the red color in this map shows that where we have a highest concentration of the renewable energy sources, and at the same point we have a plenty of excess of the seawater over there. It means if we are able to utilize this seawater to produce the hydrogen using this renewable energy, this will become the game-changing scenario where we will be producing 100% green hydrogen, and there will be no threat for the survival of life. But the challenges comes. So for the first thing, what we need to do, we need to treat that seawater, because seawater has a different kind of metal ions, non-metal ions, a lot of other compounds, and it also have a biological contaminations and a lot of molecular biological life over there. So how we can utilize if we start deionizing that one? Yes, desalination and deionization is not contributing much because they are very well established processes, and they can easily provide the clean water for the electrolyzer technologies. But the reason is that for that we need a large quantity of water to be produced. It means we need to install big plants that is not suitable at the cost at the ports or at the coastal zones to be installed, and then becomes a limitation. The entire hydrogen production should be at a one point because we can only produce water at that point. So we need to develop a system that it is free from the desalination. We can directly feed the seawater into electrolyzer. That will boost the small business. That will not limit the capital cost involved for the developing countries. So everyone can be independent to produce their hydrogen depending on what they need and how much they need. So in this way, the entire world can move or shift towards the green fuel rather than being dependent on again on the developed countries or at a very specific countries which can produce the hydrogen. And then our first aim is if we can remove the desalination step, that we can boost the small business, we can make it affordable for everyone to produce hydrogen. Second, of course, if we want to produce hydrogen and we want to meet that it is a cost effective and everyone can afford it, we need to develop the efficiency of electrolyzer system. That can only be improved if we have better catalyst and systems, and then we need to improve the operational life of them. And ultimately what we are doing, that these systems should be integratable with the renewable energy sources, and so that we are producing green hydrogen. And third, we are thinking if we are utilizing direct seawater, it can help us to capturing the CO2 that we already produce in the atmosphere, so that we are not only shifting towards the green energy or a green hydrogen, we are also eliminating the already polluted environment, and we are trying to clean it, so that we have a dual advantage. One, we shift towards the green fuel, and the one second, we are also cleaning up the already polluted environment. And then at the end, we have a very clean environment friendly discharge that can go into the sea bag. However, when we talk about the direct seawater splitting, there is a lot of challenges on the both sides of the system, on the anode side and the cathode side. On anode side, we have an competitive reaction. We call them a chlorine evolution reaction instead of oxygen evolution reaction. And chlorine evolution reaction is a more preferable to happen at the anode side. So initially it was thought that okay, chlorine is also very valuable product. If we start producing chlorine, it's fine, we can use them for the industrial applications. But to meet the hydrogen demands, the chlorine amount will be huge. It will be 400 to 500 million tons of chlorine we are producing every year. That is excess of the world consumption. That will be going into the atmosphere, and that will be another greenhouse gas. So might be we will be getting rid of CO2, but we are producing another pollutant into the environment that may be a more toxic and more dangerous in future. So what we need to do.
Can you please wind up in just 5 minutes?
Sure, I will try. And that will be another big challenge, how we can tackle this one. So we have to make sure that we are not producing any chlorine. But on the other side, when we talk about the cathode, we have a lot of metals over there. They are the positive ions. They compete with the proton and they start getting deposited on your cathode side, and with the passage of time your catalyst dying, and there's a performance compromises, and the system stability is compromised, and you are not producing with the same efficiency what you are needing. And we know that nanotechnology has helped us to modify the different kind of materials. So we also utilize the same technique. We start developing different kind of catalysts. We start with a simple catalyst, like we know molybdenum oxide is a very good catalyst. We try to do some sort of a defect engineering, and once we did it, we found that defect engineering is improving the performance by bringing more and more active sites. But even if we look at the performances, these performances are not so good even in a fresh water that we can implement into any industry. The Then what we did, we start further improving that defect engineering by functionalizing them with the different kind of smaller molecules or with the atomic dopings. We found that performances are improving but are not very significant. So we need to think bit more, and we need to bring something more into the system. And then we start designing the materials at atomic scale. We start producing the very thin 2D sheets. We start creating defects into that one, and then we create different kind of atomic dopings that are very well aligned in the system. And once we apply that kind of material and we did different kind of a characterization. If you look here, they showed that a lot of morphological and electronic structural changes happen with this kind of modification, and ultimately we are getting very good performances, and the system is very stable. But still, if you look at the performance here, they're achieving very low current density. No doubt they required very low over potential to achieve these current densities, but still are not what industry need at least half a ampere to perform or to split the water or to produce the enough hydrogen that can meet the requirements. Then we start thinking about how we can modify that one. Then we try to bring different kind of materials together, what we call them heterostructures. These heterostructures are not simply bringing two different materials together. We work and we think that how we can change the properties of both materials so that we get the super structure that perform exceptional. That idea comes from our one of theoretical calculation what we are performing. We put two materials together and we found that there is no performances. But when actually we did experimentally, we found there is a lot of performances coming up. Then we found why. If you look at this structure, when we put zinc oxide over silica, there is no change happens in those materials. But once we create a connection between these two materials, you find the polarization is occurring in the zinc oxide. That shows that this kind of a connection at the interface is changing the entire property of the material. And we use this concept to build different kind of a heterostructures to be utilized as electrocatalyst for water splitting. And the first attempt was we utilize the same molybdenum oxide, we bring it with the iron oxide, make their heterostructures. Once we combine together, we found that they have a sort of a physical connection over there where we have electron density rich interface, and that interface is giving us exceptional performances for the electrocatalytic water splitting, and we are achieving current densities of around 1 ampere. But however, when we check at their stabilities are not very useful. But we try to figure out what are the active sites in such a structures, and we found that once we bring these structures together, one act as a protection and other act as active sites, where we found that molybdenum oxide is a very active point and iron oxide is protecting it as from the different kind of harsh condition in the seawater. Then we think, okay, might be the both. If we are utilizing both inorganic materials, they are not performing well, so we need to generate different kind of heterostructures. We start working with the inorganic organic heterostructures. If you look here, once we apply this kind of inorganic and organic heterostructures together, they have a no impact of different kind of polluted waters. We provide them a fresh water, we provide them a seawater, we provide them wastewater. All kind of waters, they perform exceptional. They perform very high. The current outputs goes to 2 ampere. That is 4 times what industry needs, and the over potentials were extremely low, and they are stable over more than 2000 hours with 100% stability. And if we look after stability, their morphological and structural performances, they remain 100% same.
Sorry for interrupting you. We have a short time of period. Can you please wind up?
Sure. I'm just going through that one. And then of course, if there's no time, I will skip all these slides that that shows how the progress goes for the different kind of materials what we built, and we check them for the no chlorine production, no hypochlorite formations, and they have a high anti-corrosion properties to be utilized in seawater. And we explore in depth their mechanisms, how they perform, how they can go into details, and then we understand their mechanisms, what are the basic criterias that protect them from the anti-corrosion activities, they protect them from the chlorine attack, and make them very effective to be utilized in the direct seawater catalysis. And we found that with the different kind of modifications, we are attaining very exceptionally highly stable materials which can operate much higher what needed by the industry, and we can implement it. And then this is again showing the different kind of water splitting reactions and then their mechanisms. They are showing that how we can surpass those kind of requirements which industry needed, and there will be no impact, and we can produce these materials in a high purity in a large quantities even in our lab scale, so they are easily scalable. And then we did some sort of a performance analysis and cost comparison, which shows that they are 1,000 times cheaper, and they are several hundred times better than commercial catalysts in the market. And this is our roadmap how we are implementing this into the industry. And at the moment we can even mitigate the CO2 from the environment, that is 0.884 kg of CO2 per liter of our electrolyzer discharge that we are utilizing. And we are working with the different industries at the moment to commercialize different kind of catalysts. From all these catalysts we already have a 5 patents that is already 2 of them is already licensed to the 2 different industries, and we are working on 3 others to scale up and make them be capable for the commercializations. And being a researcher, I believe that the researchers can't do anything independently. They need to work with the technologists. If when they work with the technologists, they understand the real challenges that industry is facing. When the industry and the researchers both work together, they can really solve the different problems. And what we did here, we start developing this kind of a relationship with the industry, and now we are at a stage where we can claim that we can produce a sustainable hydrogen. And our this work goes a huge interest from the media, from the public, and from the industry. And at the end, I would like to thanks, of course, all this work is done by this beautiful team, and their hard work is ultimately paid off. And we have a different industry partners who fund us, who take up the technologies for the commercial application. Thank you so much.
Thank you very much, sir. If you have any questions, then write in the comment sections. Okay, sir.
The Department of Chemistry at the University of Education, Lahore, is a thriving hub of research, sustainability, and innovation. With a dedicated faculty and a passionate student body, the department is emerging as one of the strongest in the university. fostering a culture of curiosity and inquiry. The department's research efforts are also focused on sustainability and innovation, with a special emphasis on addressing some of the most pressing challenges facing our planet today. The students in the Department of Chemistry are known for their energy, enthusiasm, and active participation in a variety of extracurricular activities. These students are not only dedicated to their academic pursuits but also have a passion for innovation and creativity. The Department of Chemistry's seminars are designed to be highly interactive, fostering an engaging and dynamic environment for participants to share ideas, ask questions, and collaborate with fellow attendees.
died a year before. He warned the humanity, he warned the humans that you have to quit this planet Earth due to some reason, maybe in 1 or 2 centuries. And one reason maybe due to climate change. That if climate becomes so hot, this planet becomes
सब कह रहे हैं लेकिन
than 7,000 glaciers we have in Pakistan. That area is called the third pole of the world due to those glaciers. Now, speed of melting of those glaciers is being very fast now. All of our water, which is either underground or on the surface, that is due to those glaciers. So if those glaciers are melting very fast, and that is a sign of danger for Pakistan. So there are health issues related to heat. There are our crops are being disrupted, no water, some I would say disturbance in weather patterns. So many our rivers, they have been dried. You just forget Satluj and Beas. You might not be knowing even the names of Satluj and Beas. Those were two rivers of Pakistan. But even in Ravi and even Chenab, you will see this is the condition. Hardly there is any water. So there are drought areas in Balochistan, in Sindh. Uh, then there are floods. People are being dislocated. Infrastructure is being destroyed. Bridges, roads, cities come under water. So there is a lot of migration from those areas. People can't live over there. Then there are droughts and famines. No more water, no more livestock. Livestock is being affected. So these are the signs, the dangers which we are looking in last 2, 3 decades in Pakistan. And every factor is interconnected with each other. And most of the factors, they point out to economy of Pakistan. And then economy is creating unemployment, poverty, brain drain, and social unrest in Pakistan. So this is the condition which Pakistan is suffering due to global warming in last few decades. Now we come to the second part, that what are the strategies which scientists are planning, which scientists are thinking to reduce the global warming. There are two types of strategies. One is the removal of carbon dioxide from the atmosphere. There are certain ways and means to remove carbon dioxide, just like mechanical removal and underground storage of carbon dioxide. Then afforestation or reforestation, because plants are the best sources to absorb carbon dioxide. Then soil carbon sequestration, and then ocean fertilizer. So this is the, you can say, first type of strategy. Second type of strategy is that just we, that is okay, I'm saying you can remove the carbon dioxide by somehow, but if you keep the planet cool first hand, so that is again, I'm going to say, release from the global warming. So people are thinking to put certain ways and means to keep the heat away from the sun. For example, planetary sunshade and lenses, marine cloud brightening, stratospheric aerosol injection, high albedo crops and buildings, thinning of cirrus clouds. These are the strategies we shall discuss briefly one by one. So first we go to the carbon dioxide removal by direct air capture. That is called DAC, that is direct air capture. That is the technology which directly removes the carbon dioxide from the atmosphere. That use high-powered fan and air is drawn into the processing facility and carbon dioxide is separated through a chemical reaction. And then it is either stored underground or converted into some other compound. You can see a huge structure of big fans and they are blowing the air and bringing them to a separation of carbon dioxide. So this is just, I must make it clear to you that all these strategies, they are not being practiced so far, all these strategies. Some of them are in a state of, you can say, pilot scale practicing. सारी की सारी strategies जो है वो अभी तक practice नहीं हो रही. So every strategy, every proposal, every suggestion have some challenges, have some risks. For example, this direct removing, that is most expensive. It's not easy to make it such a huge structure. Then carbon dioxide is not more than you can say 4%, 420 parts per million. So the concentration is very, very low. So it's very difficult to remove carbon dioxide from the air. Although it is possible, but it is difficult. Then high energy is required to suck the air and separate the carbon dioxide. Then a large number of high efficient and expensive plants are required to implement this strategy. Second is afforestation and reforestation. We can put more forests, more plants, or we can revive the old plants, old forest. You know that plants are the very good sinks for carbon dioxide. More plants, less carbon dioxide, because you know the photosynthesis. Photosynthesis is the process by which carbon dioxide that reacts with water and form the energy, form the glucose for the plant. So more plant you see, more uh, carbon dioxide you will take away. So another is soil carbon sequestration. So whenever you have plants like some crop or something like that, and if you blow it when it is very short, and then the green material, then the carbon that gets into the soil, and when they die, they decompose, and carbon remains attached with the soil. So, soil carbon sequestration have the ability to reduce carbon dioxide at the lowest cost because those plants are carbon materials. Soil carbon sequestration would improve the soil health and increase the crop yield. So, if you put such crop into the soil and then you again use it for agriculture, that will give you more good crop. So soil carbon sequestration is possible, but not all the time. Ocean fertilization. Scientists are thinking to plant some, you can say, green material, some marine plants, some algae. आपने देखा होगा ये बाल बात जो वाटर बॉडीज होती हैं उनके ऊपर छोटे छोटे ग्रीन प्लांट्स हैं वो नॉट प्लांट्स बट वेरी 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 स्मॉल मैरीन प्लांट्स वो आ जाते हैं ऑटोमेटिकली. So scientists are thinking to put fertilizer, ocean fertilizing by putting in nitrogen, phosphorus, urea, so that the phytoplankton produce themselves on the level of the sea, and then those plants will definitely capture carbon dioxide from the air, and the same will happen as the plant on the surface of the earth does. So these phytoplanktons are very tiny marine plants that form the base of food web in the marine life. So the nutrients like nitrogen, phosphorus, urea, they will prompt algal blooms and they will absorb more and more carbon dioxide from the air due to photosynthesis. But I look at that, I'm going to say you can see that algae or those microplants, they can cover the whole water body in a very short time. So, but there are again some risks of this ocean fertilizer. For example, eutrophication may occur, which can reduce the oxygen levels in the water. Water always contains a few ppm of oxygen, which is actually the due to that survival of aquatic life is possible. So, if you put artificial phytoplankton, that may become some undesired algal blooms, and the algae becomes so great, so enormous that it might be difficult for you to control that, right? So this is also a risk. So you can also change the global nutrient distribution or biological productivity within the ocean. You can change. So it also has less potential to reduce the carbon dioxide. You can see aquatic life may be affected if you put artificial nutrients just to promote the algae on the sea surface. That may affect the oxygen level, that may affect the sunlight, and both of these factors may affect the aquatic life like fish and other things. Another strategy is to protect the earth from solar heat. कि हीट जो है धूप जो है सूरज की लाइट जो है उसको ना आने दिया जाए या उसको कम आने दिया जाए जमीन तक. Definitely that will be earth will become less hot. So this is called SRM, that is solar radiation management. Again, the scientists are thinking different strategies to do this. One strategy is that is stratospheric aerosol injection. That we put some material, some particles in the stratosphere so that the radiation from the sun that comes and strikes to those particles and gets back. That should not reach to the surface of the earth. This actually, look at that. For example, if these are the, you might not see that, there are but very small particles in the stratosphere. So if you put some aerosol, put some sulfate-like things, and they make a layer on the stratosphere, then some of the light of the sun that may reflect back. So this is the stratosphere aerosol injection, and that may cool the earth a little. But again, there are risks. Again, there are problems. For example, if you do that, you will disturb the seasonal weather patterns. You may lead to widespread flooding or drought also. And in other words, you may disturb the nature more if you do that. So, because in stratosphere, the things are not in our control. So, if the sunlight is disturbed, then food supply will be disturbed, crops will be disturbed. Ozone layer in stratosphere, that may also disturb. Then there is a strategy that some shade, some curtain should bring about the between the sun and the strategy that might reduce the light, the sunshine, and that will keep the earth cool. So look at that. These are the strategies which still are in just you can say in mind or in say in very early stages, that how the earth can keep cool for coming decades, right? It's not easy to put some curtain between the sun and the earth, or put some lens between the sun and the earth, but the things are common in you can say mind, in idea. So these are called geoplanetary sunshades in space. So similarly, geoplanetary lens, they are thinking to put some a glass shield or few millimeter thick that could act as a lens. So what that lens will do, that lens will divert the light into the space, and you can see that that is the sun, that is the earth. So if here is the lens, so that will divert the light from the sun, and the earth will become less cool. And similarly, these strategies, either a shade or a curtain or lens, that has also its own problems. For example, the first problem is that construction of such lens or such shade is not easy job. Then to transport that curtain or that lens between the sun and the earth is not an easy job. So it may require a lot of money is required. Then they may be damaged by space rock, and then it take too long for implementation. But still, it is one of the very important strategy what we are doing. This is very important that you know that white things, silvery things, bright things, they reflect the light more. And black things, dark things, they absorb the light more. So if sunlight comes, strikes on a ice cap, maybe 90-95% light that goes back. But if that sunlight comes on a sand or the road which is black, maybe 80-90% radiation will be absorbed. So heat is produced when radiation is absorbed. Heat is not produced when radiation is reflected back. So albedo is actually is the quantity, or you can say the amount of light which is reflected back. So on Earth, you can see there are so many things which may be black, which may be dark, which may be bright, which may be white. So the amount of energy reflected back by the surface is called albedo. So, for example, the forest trees, plants, they have an albedo of about 15%. So 50% of the sunlight that hit the forest is reflected into the space. Fresh snow or the ice cap, on the other hand, have a albedo of 90%, which means that 90% of the sunlight that hits the snow cap peak is reflected back. Now you can see the various objects, for example, the road, for example, the ice cap, for example, the housing, they have different value of albedo. More the thing will be white or bright, more it will reflect back and more albedo it will have. So let me start from the clouds. You have seen white clouds, you have seen black clouds. So white clouds definitely have more albedo. They reflect the light more. Why the clouds look black? Because they absorb the light. They don't reflect back. So, and why the clouds look white? Because they reflect the light back. Can we convert the black clouds to white clouds? The answer is yes. So the scientists, they are thinking on that by converting the black clouds to white clouds, we can reflect the sunlight back. So they are experimenting on special clouds which are called stratocumulus clouds that can be easily brightened by spray salt. तो वो बादलों पे जो है वो साल्ट जो है उसको बखेरेंगे, salt water in form of say sea water, और उससे क्या होगा? The cloud will become white. Because cloud, the color of the cloud or the absorption of light, it depends upon so many things. That what is the type of the cloud, what is the seeding droplet, what is the condition of the condensation. So cloud albedo may be changed, or you can say, in other words, black clouds may be converted into white clouds. So scientists are experimenting on marine clouds. Marine clouds are not very high. They are just 100, 200, 300 feet, 1,000 feet high. So one can easily spray seawater on them, and you can make them white because you are actually producing condensation nuclei on those clouds. Now you can see they are experimenting by spraying the salt water on the clouds which are very not very far, not very high on the especially on the in the cloud. तो ये एक्सपेरिमेंट जो है वो हो रहा है और इससे क्लाउड्स का एल्बेडो जो है वो चेंज किया जा रहा है एंड द टेक्निक इज कॉल्ड MCB, that is marine cloud brightening. There are again risks. No strategy is free from risk. For example, that may be implemented only in limited area, or marine flora and fauna, the aquatic life, that may be disturbed. That may affect other climate and weather patterns. So, then there are another types of clouds. You might have seen them. A very high cloud, sometime in the sky, and they are called cirrus clouds. There are 8 or 10 types of clouds if you go to meteorology deeply. So these cirrus clouds, they are very high in the sky, about 9-10 kilometers. What is the problem with these clouds is that they behave just like carbon dioxide. They trap the radiation emitted by the earth. So actually they are increasing the temperature of the earth. So if you convert the nature of these clouds or remove them, then you are cooling the earth. So people are also trying to these cirrus clouds, which are short, detached, hair-like clouds found at the high altitudes. So they trap the heat. So scientists are spraying different chemicals on these clouds through drones and trying to either change them into normal clouds or removing them from the sky. So this is called thinning of cirrus cloud. Then scientists are thinking to put artificial foam bubbles on marine, on oceans, and they make the ocean white. and that will again change at the albedo, and the sunlight that will come to the ocean and that will be reflected back. So water will absorb less heat. So that is ocean mirroring. Millions of very tiny micro bubbles are formed. You can say a sea foam would reflect away the sunlight. So the reflectance of ocean foam can be more than 10 times higher than the ocean itself. Ocean आम तो जिसपे है जो होता है वो blue होता है, black होता है. But if you turn it white, definitely it will turn the sunlight away. Then microbiologists, they are producing crops of bright color. Now you see, this is the same crop, but the color is different. So definitely, this type of crop that will reflect the light more back toward the space, and that will not be absorbed. So high albedo crops, high albedo trees, high albedo plants. That is the job of microbiologists who are thinking on that. Then buildings. Uh, if you put the building roof white or which can reflect the light back, that can reduce a lot of heat from the sun. So high albedo buildings are also in process. Now, a few issues concerned to our society. For example, a lot of people nowadays are using solar radiation. You may ask that what is the effect of solar panels if you put it on the roofs, how it will increase or decrease the uh, radiation from the sun. Actually, the solar panel is I must say, a bit photo emissive, that it creates a little heat around that roof or around that place or region. But because there are so many other advantages, it is a renewable source of energy, zero emission of greenhouse gases, displacement of fossil fuels. So due to these advantages, it can overcome that little heat which is emitted by the solar panels. So it is still, you can say, useful. Then this one thing I would like to bring into your notice. Nowadays, it's a fashion to have a black car, black dollar, black big car. So black car absorbs much more heat as compared to a white. If you park both cars of the same company, same dimension, in same conditions, the temperature of the black car would be 10 times higher, not 10 times, sorry, 10 degrees higher than the white car. So always think about the color of the car whenever you're going to buy the car. Then white roofs versus black roofs. We never think on these lines, but if we make our roof white by just a whitewash, the temperature of your house will become 2, 3, 4 degrees less as compared to if you put something black on your roof. Okay, thank you very much.
It seems students are very happy they understood everything. We can take few questions, please. Yes, please. बच्चों में माइक दीजिएगा प्लीज. Alaikum sir. I So I just want to ask us, all these strategies are under experimental techniques. Then can we think that these can be implemented in the future or not, as their advantages are less as compared to their disadvantages?
इसके yes, I've told you side by side that every technique has a risk, some disadvantage. But as so far, these techniques have not been applied at a large scale, but they are just at experimental lab, right? But sometimes it happens that advantages, disadvantages, especially, they are not foreseen timely. For example, every chemist is nowadays preparing nanoparticles, but maybe after 20 years, people will try to wipe down the nanoparticles, उनको इकट्ठा करते फिरें, उनको remove करते फिरें, how to remove nanoparticles. So it's never, I'm saying, these strategies, साइंटिस्ट अभी वो सोच रहे हैं, प्लानिंग कर रहे हैं, कुछ टेक्निक जो हैं वो एक्सपेरिमेंटल स्टेज पे आ गई हैं, जैसे वो मैंने बताया मैरीन क्लाउड्स की वाइटनिंग का, तो वो ऐसी टेक्निक जो है उन पे काम हो रहा। लेकिन ये जो वो कर्टन वाली थे मैंने आपको बताई, लेंस वाली बताई, उस पे थ्योरेटिकल काम जो है वो हो रहा है, लेकिन अभी तक प्रैक्टिकल काम उस पे नहीं। ओके, थैंक यू वेरी मच।
Our next speaker is Professor Dr. Irshad Hussain. He is Chair of Department of Chemistry and Chemical Engineering, SBA School of Science and Engineering, Lums, Pakistan. He is very young and very decorated scientist of Pakistan. He has so many awards in his credit, like he got 2 gold medals in chemistry by Pakistan Academy of Sciences back in 2007 and another one in 2014. And he is the fellow of Pakistan Academy of Sciences. He is the fellow of Royal Society of Chemistry, UK, and a fellow of International Engineering and Technology Institute. And he has recently been named as PIFI Distinguished Scientist by Chinese Academy of Sciences. So today he is talking about functional nanomaterials, turning the size and surface chemistry for applications in biomedical science, renewable energy technologies, and environmental remediation. Over to you, Doctor.
Assalamu alaikum. Thank you very much, Dr. Shazia, for the kind introduction, and especially saying me so young. I'm not that young, by the way. So before I start, I would like to really thank the organizers for the invitation for this lecture. Most of you probably know that I work on nanoparticles that Dr. Jamil was mentioning, and try to use those nanoparticles as building blocks to make new materials and then explore their applications in biomedical sciences, renewable energy technologies, and environment. And some of those are being explored to address the challenges, climate change challenge, global warming challenge, and that I will discuss as well. So here is the outline of, it's not working. ये connected है कहीं पे? जी। तो जैसे मैंने बताया, मेरा काम नैनो पार्टिकल्स पे है. तो what we do is we prepare those nanoparticles with perfect control over their size, shape and surface chemistry. पार्टिकल्स बहुत सारे लोग बनाते हैं और जैसे डॉक्टर साहब बता रहे थे मैनी ग्रुप्स आर इन्वॉल्व इन दैट. लेकिन हमें ये पता होना चाहिए कि प्रॉपर्टीज जो हैं नैनो पार्टिकल्स की दे रियली डिपेंड on their size, shape, and surface chemistry. So whatever technique you use, you should make sure that particles you are preparing, they are very uniform in size, very uniform in shape, and they have controlled surface chemistry as well. So I will talk about how we prepare those nanoparticles or nanoclusters. I will use the term nanoclusters. These are the particles which are even below 2 nanometer. In some cases, they are even below 1 nanometer as well. And if the size is above 2 nanometer, then we usually call them nanoparticles. Then I will talk about some of their applications in biomedical sciences, renewable energy technologies, catalysis, and environment. And all this would be basically the work that is being done in my group in collaboration with various collaborators across the globe, USA, Europe, and nowadays mainly with China. We know that there are different physical, chemical, and biological methods to prepare these nanoparticles. The method that we use is based on very simple chemical reduction approach. इसमें हम क्या करते हैं? We start with metal salts and then reduce metal ions to metal atoms. अब ये metal atom इतना छोटा है, you know, that it has huge surface energy. At any given time, there will be millions or billions of atoms which are produced, depending on the concentration of that metal ions, and then they would immediately collapse to reduce their surface energy to initially make these small metal nuclei of few atoms. And these nuclei then grow into bigger particles. So basically, there are two processes, nucleation and growth. And if you can control these two processes, you can very easily control their size, shape, and surface chemistry. These particles are still smaller than 100 nanometer, so they have, again, high surface energy. They have tendency to agglomerate to make bulk materials. So once these particles are formed, you need to immediately stabilize them. And there are two approaches by which we can stabilize. One is to coat these nanoparticles with molecules which have positive or negative charge. So in that case, all particles become negatively or positively charged species. And we know that similar charges, they repel each other, and that's why they stay away. So this is particularly important when you want to use these nanoparticles for biomedical applications, because these loosely bound molecules can be easily replaced with biomolecules like DNA and proteins. And then you can use those for different applications. If you want to use these nanoparticles for nano devices, nanoelectronics, and optics, you really need highly stable particles. And that can only be achieved if you covalently attach long chain molecules through thiol bond or amine, and then due to steric hindrance of these long chain molecules, these particles would stay away from each other. These are extremely stable particles. You can even dry them and store them for years. And depending on the chemistry, functional groups of these kind of molecules, their solubility can be tuned as well. So here is just my initial work when I started working during my PhD on these metal nanoparticles, especially gold nanoparticles. So at that time, there was not even a single method which can be used to prepare particles which are very uniform below 5 nanometer. So what we did is we prepared this polymer And by controlling the ratio of this polymer to gold salt, for example, we were able to make very uniform nanoparticles. They could be 1 nanometer, 2 nanometer, 3 nanometer, and 4 nanometer, just in one step method. And then you can replace this polymer. By the way, this hydrophilic carboxyl group makes these particles soluble in water. And after this synthesis, you can remove or exchange this polymer with alkane thiol molecules and then transfer them to from aqueous to organic solvent. And they retain their optical properties as well. Many of you probably know that this absorption of gold particle is due to surface plasma resonance band, which is due to collective oscillation of electrons at the surface, which is much different phenomena than we observe when different organic molecules, for example, absorb light or they look colored. So this is not due to electronic excitation, it is due to surface plasma resonance band. And we also noticed that when particle size decreases below 2 nanometer, they lose their surface plasma resonance. It means they lose their metallic properties as well. They become semiconductor, and even if they're small, they behave like gold molecules, like not like gold metal. Okay, so here in this case, what we did is we designed these polymers in which single polymer has multiple thiol groups. And as I mentioned before, this thiol has very strong affinity with metals. And it basically stops the growth of these nuclei, and you can then make particles which are smaller than 1 nanometer, even few atom clusters using these kind of polymers. And using this, we were able to make copper nanoclusters, silver, gold, and platinum, which in this size regime became fluorescent in nature as well. We know that metals are generally not fluorescent, but if you reduce their size and control their surface chemistry, then they become fluorescent. And interestingly, they do not photo bleach easily. So they have very interesting applications in bioimaging and biosensing applications. So due to limitation of time, I cannot really discuss all their applications that we explored for bioimaging and biosensing. But if someone is interested, we can discuss that as well. So here is just one example in which we prepared the silver 44 nanoclusters. Silver 44 means these are nanoparticles which are atomically monodisperse, and they contain only 44 atoms of silver. Each particle would contain 44 atoms of silver. And interestingly, they absorb major portion of sunlight from UV to visible to NIR. And this absorption, they are extremely red in color. This is not due to surface plasma resonance, because in this size regime, the silver is not metallic. This is due to now HOMO-LUMO transition. And initially we thought that they could be very useful to harvest sunlight for solar cell applications. But later we found that they are not really that good, because it was very difficult to make very uniform thin films of these materials because they were water soluble. So we started exploring their applications as antimicrobial agent. We know that silver is antimicrobial in nature, but it really depends how antimicrobial is that. It depends on the size, shape, and surface chemistry. And in this case, we found that these silver 44 nanoclusters, which are coated with these aromatic ligands, they're able to treat some sexually transmitted infections by multi-drug resistant bacteria, which are otherwise very difficult to be treated using traditional antibiotics or even larger particles. So we found that they are very effective to kill multi-drug resistant bacteria. But here you would notice that due to this carboxylic group, they have negative charge. Bacteria surface also has negative charge. So there is not much interaction, electrostatic interaction between these particles and the bacteria. And in order to enhance that interaction, we further coated them with some cationic polymers, like polyethyleneamine, for example. And we noticed that they became even more effective antimicrobial material. So this highlights that surface chemistry of these materials is really important. So then one of my PhD student further explored that how two different sizes of silver nanoparticles, for example, having same surface chemistry, 2 nanometer silver nanoclusters and 10 nanometer silver clusters, they affect FAPC fibrillation. We know that it is difficult to kill bacteria when they hide themselves in biofilm. And FAPC protein play a very important role in the formation of biofilm. So we noticed that this 10 nanometer silver particles are quite effective to inhibit FAPC fibrillation much more than 2 nanometer stuff. But still 2 nanometer silver nanoclusters are more effective to kill bacteria in the biofilm, especially because due to their smaller size, they can penetrate through the biofilm and reach to the bacteria surface. And later, one of my PhD students, Shazia, she wrote this review article, very important and very simple review article, in which we highlighted that how surface chemistry of these materials is important when you design these materials for antimicrobial applications. For example, one important thing is they should have positive charge so that they can effectively interact with the negatively charged bacteria surface. And second, they should have some hydrophobic components so that they can get into the bacteria by passing through that lipid bilayer membrane. So this is very interesting and very simple review article, especially for the beginners who want to design materials for antimicrobial applications and want to know that how surface chemistry is important in that case. We also prepared some iron oxide nanoparticles as artificial enzymes to detect bacteria in drinking water. Here, these iron oxide nanoparticles have redox properties, which are very similar to horseradish peroxidase enzyme. So when you add these nanoparticles to this substrate, which is pyrogallol, it is immediately converted to red product. But if you functionalize these nanoparticles with dopamine to render them positively charged iron oxide nanoparticles, and then add it to drinking water, bacteria in drinking water will immediately cap these nanoparticles, and then this yellow substrate will remain yellow in color. And by using this very simple phenomena, we developed this colorimetric assay to detect bacteria in drinking water. Unfortunately, it is not that sensitive at the moment that it can be used practically. Another applications of these nanoparticles is, drug delivery applications for as nanocarriers to deliver anti-cancer drugs to their targets. Recently, not recently, about 10, 15 years before, Professor Warren Chen, University of Toronto, he was Chinese professor, they found that if particle size is 80 nanometer, for some reason, these particles are easily taken up by the cancer cells. But among nanomaterials, we know that 80 nanometer is quite a big particle. It has large metal contents, and it is very difficult to, not even possible to biodegrade metals. So what we did is, there was interest to develop particles of the same size, but with less metal content. और वो कैसे कर सकते हैं? By making these particles porous in nature. उसमें metal content कम हो जाएगा, surface area ज्यादा हो जाएगा, and we developed various one-step methods to prepare particles of that size regime, which were porous and higher surface area, which can you use for as nano carriers for the delivery of anti-cancer drugs. So that was some of the applications related to biomedical science. For renewable energy technologies, we know that for fuel cell technology, so among the green technologies, we know it is solar cells or fuel cells. And for fuel cells, we know we need to use hydrogen as a fuel, as a chemical fuel to convert into electrical energy. अब प्रॉब्लम यह है कि हाइड्रोजन को कैसे प्रोड्यूस किया जाए एंड वन ऑफ द ग्रीन मेथड is to separate water molecule to hydrogen gas. But unfortunately, the amount of energy which is required to separate water molecule to produce hydrogen gas, that is more than the energy you could harvest from the produced hydrogen gas. So you need to use some catalyst to reduce that energy. And different electrocatalysts and photocatalysts are being explored for that purpose. And platinum, iridium, and ruthenium-based catalysts, we know they are among the best electrocatalysts for this purpose. But these are very precious metals. They are not earth abundant. So we, few years before, 7-8 years before, we started looking into transition metals which are earth abundant and whether they can be used as electrocatalyst for water oxidation to produce hydrogen gas. So these are all articles from our group. And here is our first article that was basically using nickel nitrate and reducing this with carbon monoxide in the presence of phenylethyl thiol. Again, you note we have thiol functional kind of ligands. We were able to prepare two types of nickel nanoclusters, which were extremely small, smaller than 1 nanometer. One particle contains 4 atoms of nickel and other contains 6 atoms of, and they were atomically monodisperse. Here, because once the particle size is so small, it is extremely difficult to characterize them. So we need to use the techniques that we normally use to characterize organic molecules, like high resolution mass spectrometry or high resolution kind of single crystal XRD. And for that purpose, we using single crystal XRD, we confirm that one particle contained 4 atoms of nickel, other contained 6 atoms of nickel, and they were found to be effective to electrocatalyze water oxidation to produce hydrogen gas with an onset potential of 1.51 volt. This is not very good, but at least it highlights the potential of these materials as electrocatalysts for these type of applications. Problem with this was because they were extremely small and they were coated with some hydrophobic ligands. They were not very stable and not very effective as well. So later what we did is we functionalized graphene oxide to produce thiol functional group onto this, which increased this electrical conductivity as well, and then covalently attach these very small nickel nanoclusters onto that. So this is covalently attached nickel nanoclusters on graphene oxide. It provides better electron transfer between nickel particle and the graphene oxide, and it was found to be very good electrocatalyst with an onset potential of 1.46 volt. And it was quite stable up to about 90 hours. Later, in addition to nickel, we also produced copper and cobalt oxide nanoclusters, and we found that they were also effective, but with an onset potential of 1.52. That shows that nickel in this system is a better electrocatalyst than cobalt or copper oxide. So later what we did is we used these nickel nanoparticles and nickel nanoclusters as catalyst to grow carbon nanotubes to develop bifunctional catalyst, which can catalyze both oxygen evolution reaction and hydrogen evolution reaction in wide pH range. And we noticed that by controlling the size of these nickel particles, we were able to somewhat control the diameter of carbon nanotubes as well. So bigger is the particle size, bigger is the diameter of carbon nanotube, and they were found to be very good bifunctional electrocatalyst for water oxidation, which can catalyze both HER and OER in wide pH range. The most stable and most effective catalyst in this case was based on cobalt nanoclusters in nitrogen-enriched mesoporous carbon. And we found that in that case, we achieved the lowest onset potential of 1.44 volts, and it was even stable beyond 125 hours. So this was the most stable electrocatalyst based on cobalt nanoclusters. Being chemists, we are always interested that how the surface chemistry of these materials affect their properties. So in this case, what we did, we have nickel nanoclusters, which are alkylated, which are coated with hydrophobic ligands. And then we introduced a doped it with gadolinium. And we noticed that its electrocatalytic activity increases. It further increases if we incorporate electronegative atom like halogens, in this case chlorine. And then if we remove some of these surface ligands, it becomes even more effective because it provides more area for the adsorption and desorption of intermediates which are formed during this process. Okay, so these were all electrocatalysts. Apart from these electrocatalysts, we are also working on photocatalysts, especially photocatalysts which are based on covalent triazine framework, CTF. We know that CTF is a semiconductor material with wide band gap, and then it is usually made in the form of powders. It's very difficult to make its electrode. So in this case, what we did is we prepared these covalent triazine framework at liquid air interface to make very thin films of CTF, and then generated platinum nanoclusters onto that. And we found that it was really effective for photocatalyst for the oxidation of water to produce hydrogen gas. So very recently, just a month before, what we noticed, we know that when we prepare these conducting polymers, you need to enhance the conjugation of it. Conjugated system ज़्यादा होना चाहिए ताकि delocalization of electrons ज़्यादा हो. So in this case, what we noticed that you can improve or you reduce the band gap of CTF and increase their electrical conductivity if you use these fused monomers for that purpose. Because in that case, it remains planar. For delocalization of electrons, one requirement is that system should be planar. So these fused rings keep the planarity of these CTF, and they were even more effective photocatalysts for these kind of applications. In this case, it is not hydrogen production, it is hydrogen peroxide production in this case. Okay, so I believe there are some organic chemists over here as well, and they would know about the limitations of Friedel-Crafts alkylation process. Friedel-Crafts alkylation is usually used to alkylate these aromatic rings to introduce some alkyl group over here. So if you have one alkyl group, it actually activates the ring for further alkylation, and you end up with polyalkylation. That is kind of limitation. So we made use of that limitation by using these aromatic molecules as monomers, and then cross-linked with these dihaloalkanes, which have halogen group on both sides. It acts as cross-linker, and by controlling the number of these CH2 groups, we were able to control the pore size of these microporous polymers. And due to the very small pore size of 1 to 2 nanometer, they have very high surface area, and they have ability to store carbon dioxide and hydrogen gas. और जैसे डॉक्टर जमील अहमद साहब बता रहे थे कि कार्बन डाइऑक्साइड is the major cause of this global warming or climate change. So we thought that why not use these materials to actually capture CO2 from the atmosphere. And for that purpose, we designed this photocatalyst in which you have graphene, which is coated with titanium photocatalyst, And on this photocatalyst, we generated hyper cross-linked polymers, जो मैंने पहले यहाँ पे बताया. So that these were produced at the surface of these titanium nanoparticles, and they can absorb CO2 and then direct CO2 to the photocatalyst, where that is converted to hydrocarbon like methane gas. So this system is very useful for CO2 capture and conversion. And on this basis, we got Pak China Collaborative Project, which is supported by Pakistan Science Foundation and NSFC. And we further improve this system so that they can really become more effective catalysts for this purpose. Here are some more examples of heterogeneous catalysts which can be used for carbon-carbon coupling reaction or carbon-nitrogen coupling reaction. We know that organometallic complexes are generally used for that purpose, but in this case, we use these platinum nanoparticles on these porous spores, and we found that they were really effective for that one. So time is running short. So here is just one example. More recently, my interest is more on particles which are smaller than 2 nanometers and explore their applications. And here we just noticed that if you have copper 58 nanocluster and remove just one copper atom, this one, from the surface, you convert copper 58 to 57, which is very good effective catalyst for click chemistry. Click chemistry, you know, is very important. Last year, Nobel Prize was given on this process, and these clusters are very useful for that purpose. Here is the last 2 slides in which we developed this process by which you drop these oil in water and oil emulsions to this column, which is filled with hot iron. As they settle down under the force of gravity, they get polymerized to make these polymer beads. Very uniform polymer beads. They are highly porous, hierarchically porous indeed. And if you soak these with gold nanoparticles get into these pores, and then you can increase the concentration of gold particle, that after calcination, you remove this template and end up with pure gold beads, which are 99.9% gold and which have very high surface area. And due to their high surface area, they could be very useful electrode for electrochemical sensing of different biomolecules. We extended this approach to make palladium beads, platinum beads, and even monoliths, as they are more effective catalysts. And more recently, one of my PhD students further extended this approach to control the chemistry of these polymer beads, pore size, and then incorporate different metal nanoparticles into that, especially silver nanoparticles, basically to design a customized adsorbent to remove either toxic metals or toxic organic molecules, and meanwhile kill bacteria as well by the use of these silver nanoparticles in this stuff. So this was just the summary of the work that we have been doing. And finally, I would like to thank all my collaborators, so many collaborators across the globe, and funding agencies, and of course, my students who have done all this middle work. So thank you very much for listening. I'm sorry if I take 1-2 more minutes.
If organizers allow us, can we ask 1 or 2 questions from him? Okay. Students, please ask questions.
Sir, I have a question. Thank you for being here in this conference. Sir, as I know, the stability of the metal nanoparticles are very crucial for their unique applications. As you are talking about the stability, what does that exactly mean? You are talking about the chemical stability or thermal stability?
Well, I was talking about chemical stability in a way, because if you, the properties of these nanoparticles really depend on their size. If they are not stabilized, they will immediately collapse to make macroscopic materials, and they would lose their specific properties, which are due to nanoscale features. So my point of stability was that those particles remain individual particles They do not aggregate further to make macroscopic materials.
Thank you, sir.
Assalamu alaikum, sir.
Jiva.
Sir, as you said, you prepared a silver 44 nanocluster and nickel nanoclusters which were containing 4 and 6 atoms. So when we prepare these nanoclusters, it is dependent on the reaction condition, or we can control the number of atoms, or it depends upon the metal's capability.
Excellent question. So, like organic chemistry, this is not that easy to control the number of atoms in these particles.
Yes.
It is just coincident. For example, you use different type of thiol-based ligands in this case, end up with some particle which are very uniform, which have uniform properties. So then when we characterize, they were silver 44. So we cannot really program the synthesis to prepare 44, or if we want 55 atom cluster or 50 atom cluster, it is not possible at this moment.
Okay, thank you.
Okay. So you simply tune the reaction conditions to make particles as small as possible, or depending on what size you need, and you end up with material, and then you have to characterize that.
Yes, sir, in a single particle, 44 silver atoms.
Yes.
But by using which technique we can determine the number of atoms?
Pardon?
Number of atoms by using which techniques? We can find.
Oh, okay. So for that purpose, as I mentioned, that as you reduce the size of these particles, it becomes very difficult to characterize them. Okay, so for that purpose, you need to use techniques which are used to characterize organic molecules, like high resolution mass spectrometry. So number of atom and exact number of ligand at their surface, that is determined by basically couple of techniques, and most important technique is high resolution mass spectrometry, which gives the molecular weight of those kind of nanocrystals. And then if you are lucky to recrystallize that to make very nice crystal, then you can characterize them by single crystal XRD as well. So that will give you better idea how ligands are attached to the surface and how many atoms are there.
Thank you.
So this is combination of different tools, different techniques.
Thank you very much.
Thank you.
Sir, Assalamu alaikum, sir. Sir, I am just thankful to you for your time, and you participated in every year in our conference. This is our pleasure. I just request you to please guide our student how they can join your research group.
How can join my research group? So they need to join LUMS for that purpose. And our admissions are going to start next month. And I know every year there are few students from University of Education. They get admission over there, and that is platform to fly to US. That every student probably know that. So we have undergrad program in chemistry at LUMS since 2008, and first batch was graduated in 2012. Since 2012 till today, any of our student, undergrad student, if they are interested to go to higher studies for US, there is 100% acceptance rate. And 100%. And for MS students, it's now increasing. And last year, it was about 70 to 80% success rate as well. So every year, about 40 students graduate from our very small department, and 30 of them, they go to US on fully funded PhD programs. So that highlights. Thank you very much.
So our next speaker is Honorable Professor Dr. Shazi Anju. The title of the talk is Natural Products, a Contemporary Approach for a Drug Discovery. A brief introduction. Professor Dr. Shazi Anjum is the Professor of Chemistry Department and the Dean Faculty of Chemical and Biological Sciences, the Islamia University of Bhavalpur. She is experienced medicinal and natural product chemist. She has an excellent record of teaching and research. She has over more than she has over 143 research papers in high impact factor journals. As recognition of her contributions to science, she has been awarded with 4 international awards, which are among top 25 women leader cohort 2022 for 2 years training from Michigan State University and HEC, fellowship from Islamic World Academy of Sciences, postdoctoral fellowship from Ministry of Culture Education, Spain, and Young Scientist Chemist Award from Third World Academy of Sciences, Italy. He has also several national awards. There's a long introduction which I'm making short just because we are eager to listen to you, madam.
Bismillahirrahmanirrahim. This is the conference that is about chemistry. And in chemistry, there are so many chemistries. And I see diversity in students. So though I'm an organic chemist, but I won't talk about too much organic chemistry to make you bored. But in general, I would like to give some flavor about natural products. As you know, this conference, the theme is trends and research in chemistry. So this is fast-paced world where science is, progressing so fast that the things that look like fiction, they are reality now. So this is wondrous world of science where truth is stranger than fiction. Starting with natural product chemistry, the human being, they are using natural products for their ailments, for their cure, and still in this contemporary world, people, the pharmaceutical companies, they are using natural products for drug development. Let's see what the progress is making these natural products. What are the sources of natural products? Sources could be any natural source, organisms, plants, marine organisms, animals, insects, anything. And of course, the sources of drugs can be can be get from synthetic chemistry, from editorial chemistry. If we see worldwide, over 1/4 of the best-selling drugs, they are either natural products or they are derived from natural products. I mean, derivatives of natural products. So, all available anti-cancer drugs between 1940 to 2002 year, 40% were natural products. So, natural products are that much important. You see, if in the morning you take a cup of tea, it contains millions of natural products in it. And working on those millions of natural products is very, very challenging. Let's see what the challenges are. Before we go into the challenges, let's see how herbal products, they are getting huge market worldwide. Even the developed world, they are going more into herbal products. Like you see, the United States of America, they are using 23.3% herbal medicines, herbal drugs. And Europe, it is 38.2, and Asia 18.1, and the main contributor for this herbal product is China. China, in a very systematic way, they are working on traditional Chinese medicine. And after China, India is following China, but Pakistan is still far behind. Here is the general scheme, how natural products could be obtained and what are the challenges and how to cope with those challenges. Like, for example, starting with any living organism, including plant or animals, crude extract obtains, and then multiple rounds of fractionation, several fraction obtains, and it could lead to single component. And in the meanwhile, you can also do bioactivity evaluation. But at the first step, there is no possible, it is not possible to culture organism out of natural ecosystem. So another problem is the relevant natural products are not produced when organism is taken out of the natural habitat. I mean, if one plant is growing in northern areas and it is producing some natural products, and we try to grow it in desert, climate is entirely changed and there is inconsistency. So natural products main challenge is they are consistently inconsistent. The solution is also there that we should develop new methods of culturing those plants or organisms, new methods for in situ analysis, and as well as new methods for natural product synthesis, induction and heterologous expression of biosynthetic genes. So here, chemistry merges with biotechnology. Another problem could be for single compound. If you end up with some single compound and then there is unknown molecular target for natural products identified with phenotypic assays, and solution is new methods for molecular mode of action is elucidated. Regarding crude extracts, presence of natural products that are known, they could be isolated. And this is traditional approach that people, they were looking for some new entity from natural products. Anything that has very pronounced biological activity, it is important to identify it and make it as a drug molecule. Another problem is presence of natural products that do not have drug-like properties. What to do with that? There are several drugs in the markets. You are also repurposing that drugs for some other disease. And in nature, Allah subhanahu wa ta'ala has not created anything that has no use. So we have to find the use of that natural product. Bioactive natural products are present in insufficient amount. This is the greater challenge. You start up with kilograms of plant material or any organism, you do extraction, all those natural product chemists who they are sitting here, they know they end up with few milligrams of those compounds. So the solution is there that you ask synthetic chemists if there is some lead compound, then synthetic chemists can synthesize that compound for you. So several challenges and their solutions, we move forward. Older strategies, as I said, that people, they were focusing not on activity but new compounds, but now this trend has been changed. And modern strategies, they include bioassay guided fractionations, more focused on any particular bioactivity, and then de-replication. This is very fast technique, and it could be done in seconds of time if you have the instrument, and then fingerprinting and metabolomics. In modern techniques, as I said, that LC, HRMS, this is some hyphenated technique. And the rest of the other techniques like LC-NMR, LC is linked with NMR, so hyphenated technique again, and HRMS or MSI or DIMS, these all are the techniques that are used for de-replication of any natural product or herbal product, and in a few seconds you can get good results. And there are libraries from data search, you can also characterize those compounds. So we can control the challenges. We can have collaboration with synthetic and medicinal chemists. We do synthesis or semi-synthesis to move forward for drug development. As you know that drug development, it takes a huge investment, it takes huge time, it takes involvement of several disciplinary people. So, for example, we have so many drugs in the market. If I talk about just the Disprin, if there is Disprin, in order to make it to the market, available in the market, there are several steps. You do in vitro assay, you do in vivo assay, then you test that drug-like molecule on some small animals like rats, then rabbits and monkeys. Then at the final clinical trial, you do at human being. And by that time, it takes billions of dollars. So it is very challenging to develop any drug. This is the process where drug discovery can be seen, that medicinal plant discovery, it is guided by several bioassays of interest. And most importantly, I would like to mention here that if you're working on some plant, there is ethnobotanical information, that ethnic people, they have information that this particular plant is used for cancer or for kidney diseases. Then you test that compound in the laboratory. And at the end, you got lead compounds for clinical trials. Here are a few of my research focused areas. My research group is working on anti-diabetic medicinal plants. And my focus is not only micromolecules. I'm also working on macromolecules. Micromolecules, you all know that small molecules, that all organic compounds, natural products, and natural products are also macromolecules like proteins, amino acids, peptides, etc. They also have, they are also present in plants. So I worked on 3 plants, and I found in some plants the activity of anti-diabetic activity was due to small molecules, and in some plants the anti-diabetic activity was due to macromolecules, due to proteins. So our research group isolated proteins, and we purified that protein, and we found those proteins. We did some in vitro assays and some in vivo assays. They are going on, and in vitro assays we found them more effective, and we are trying to characterize those proteins. Some have been characterized through MS technique, and other we are trying to crystallize them. They are novel proteins. This is general figure about how quickly diabetes is spreading all around us. That in year 2000 there were 2.8% patients, and now it is anticipated by 2030 there would be more than 4.4% diabetic patients around. And the reason is our lifestyle, population growth, aging, and urbanization, and prevalence of obesity. Obesity is, of course, like our lifestyle. We don't do extra work. We just sit on a computer or tab or phone and do so many things. These are the plants from Cholistan Desert, 2 of them. Common name of this plant, Bravia procumbens, is botanical name, and common name is Vishkipra. And another one is Corporus repressus. Common name is Bhopali. And I just concluded it. I'm not presenting my all results through because time is short. And we found that each plant has sufficient amount of protein, and we did protein isolation and estimated it through Geldal method and as well as Bradford assay method. And we isolated proteins not only from leaves, we also isolated from seeds and as well as from roots. Proteins extracted from corpus repressors showed less anti-diabetic activity as compared to their methanolic extract. What does it mean? It means that small molecules, they have good anti-diabetic activities, not macromolecules. However, the total protein extracted from roots and whole plant of Bravia procumbens have great anti-diabetic potential as compared to their methanolic extract. So the another plant, the macromolecules, they are more active against glucosidase inhibitors, glucosidase enzyme. My second project is standardization of Moringa oleifera and to check its anti-urolithiatic property. I mean, urolithiasis is developing kidney stones. And Moringa oleifera, this is a very common vegetable in south of Punjab, and people, they eat it. So there is no cytotoxic effect of this plant material, but we use plant extract and we found it has very good anti-urolithiatic property. We went like bioacid guided fractionation. We checked leaf extract, root and seed extracts, and then we found that the leaf extract, they have more pronounced anti-urolithiatic potential, and then we did several fractionation, and at the end we also found lead compound. Here is the story that these are the derivatives that have very good anti-urolithiatic potential. Lead compounds even more active than commercially available drugs is shown. These are the results of nucleation of niacimycin, all these three compounds, and then aggregation results. These are in vitro results, and then crystal growth assay result to show anti-urolithiatic potential of these compounds. This is tabular form of those results that we just saw in the form of graphs. So here I conclude the second project of my student, that we got niacimycin more potent compounds than the standard drugs used in those in vitro and in vivo assays. In vitro results indicated the positive inhibitory effect in comparison of cystone. New compound Vagizinino was also submitted for in vitro anti-urolithiatic potential to determine and show to determine its proper results. And the third project, it is very interesting. This plant, Parthenium hysterophorus, it is invasive weed. And people consider it is very dangerous around us because it invades in several crops and it competes with those crops and eat nutrients of crop, and it grows itself. And from northern areas to now till Punjab, it has a very bad reputation of spreading all over. So, but I was thinking differently. I thought Allah subhanahu wa ta'ala has not created anything useless. So we thought we should find out something good out of this invasive weed. And we did several biological activities of crude extract of this plant. We did anti-urease assay, all available assays that were present in my university. We did antioxidant assays, and we found that some of the extracts of this plant, they have very good antioxidant activity. We did bioacid guided fractionation, and we found that leaf extract, it has 63.29 microgram per mole, microgram activity again, antioxidant against DPPH assay. Then we fractionated this and we found that ethyl acetate, further it has improved antioxidant activity. And finally, we found these two compounds, they are polymorph of each other, and they have In nanograms, IC50 value for antioxidant assay, and they have also very good anti-urease assay. So we subjected these compounds for in silico studies because mostly flavonoids and antioxidants, they have good potential against Alzheimer, acetylcholinesterase, butyrylcholinesterase, and other enzymes that are used to cure Alzheimer, that is beta secreterases and gamma secreterases. We did in silico studies as well, and we found these two compounds are potential compounds for Alzheimer disease. And we are also working now for in vivo model of these compounds and to evaluate them for their cytotoxicity, because it is very important whatever you say that this is drug, it is the lab results. We have to be also careful about the toxicity of those compounds. If some compound has very good profile against any biological activity and it is very toxic, then it has no use. So the next step, of course, it takes it takes hours and many days to determine the total potentiality of those compounds. So we are in the step of the final step of determining the toxicity of these compounds. And interestingly, these compounds have been isolated in greater amount. We are not short of quantity, so we can also run in vivo assays. These polymorphs, they have different color, shape, solubility, and even different biological activities, but their spectroscopic data is similar. And both compounds exhibited moderate inhibition against butyrylcholinesterase and acetylcholinesterase enzyme, and both compounds showed excellent urease inhibition, even better than standard drug. These are in silico model, a crystal structure of different beta secretase and gamma secretase enzyme, 1 FKN and 6 IYC. They are binding with our compounds and they have improved ADME. These are different binding affinity results of both polymers against gamma secretase and beta secretase. These are the results of. In conclusion, this current work suggested that compound 1 and 2 are effective against Alzheimer's disease. And they can target C and gamma beta and gamma secretase enzyme. It is still our group is working for its toxicity evaluation, and here is the acknowledgement. First of all, I would money makes the mayor go. HEC is the main funder for these projects. 2 research grants that I won from HEC, thanks HEC. Then my mentor, Professor Dr. Ataur Rahman and Professor Dr. Mohammad Iqbal Chaudhry. They helped me a lot, whatever I am today, because of all these 2 personalities. And our international collaborator, they help in spectral analysis, like Dr. Syed Adnan Ali Shah from Malaysia and Professor Dr. Hisham Ilsidi from Sweden. And of course, some of the results and characterization were also done in lumps in collaboration with Professor Dr. Ishaq Hussain. And some of our biologists, Professor Dr. Mohammad Ashraf, Professor Dr. Kaisar Jadeen, she is pharmacologist in my research collaboration, and Dr. Samina Ijaz, she is biochemist. And my PhD students, Dr. Sana, she worked on Parthenium histophorus, that was investigweed, and Dr. Wajid, he worked on Moringa olifera. And then Dr. Mazala, she is working on macromolecules and to determine their anti-diabetic activity and characterizing proteins, structure, etc. Thank you for your patience and attention. Here is a slide that shows now you cannot do research in isolation. You have to collaborate with each other. And this is the slide that when I was in Canada, my research group, they were collaborating. Some were from structural biologists, some scientists were from the lab of enzymology, microbiology, organic chemists, and they all were working on one project. They were determining the pathway of one bacteria that was producing antibiotic, hello and it was very interesting project, and they were meeting every on quarterly basis discussing different aspects of that project, and it was very interesting, and I feel very honored to be the part of that group at that time. And I learned a lot from them that if you do some meaningful research, you do it in the depth. You know, you have to cover every aspect of it. Don't do just जैसा कि हम यूजुअली पाकिस्तान में करते हैं कि अपने रिजल्ट्स के लिए कभी कान पकड़ लिया, कभी नाक पकड़ ली, और काम बस हम चाहते हैं कि गुजारा लायक हो जाए, हमारा पेपर पब्लिश हो जाए और हमारा थीसिस हो जाए. लेकिन वो इतना डीप जाकर रिसर्च करते हैं हर चीज को, तो उसकी वर्थ बहुत ज्यादा होती है. तो जब भी आप काम करें, डू इट इन कोलैबोरेशन विद अदर्स. If you don't find international collaborator, you can do collaboration with national collaborator, because everybody in their area, they are doing excellent job. But if you collaborate with them, then the worth of the paper would be increased many folds. Thank you very much.
Thank you very much. It was an excellent talk and excellent advice as well. So the house is open for questions. Assalamu alaikum, ma'am. As we talked about the extraction of the different natural products from the plant, and if we started that extraction at a large scale, don't you think that it would come in the decline of the plant?
Very good question, because if we use large quantities of plants, obviously the plant would get extinct. And especially the desert, it has very few species of plants, and extinction of one plant means a lot. We do it in collaboration with some botanists. They collect plants for us, and they leave sufficient amount of that plant that can regrow. And we chemists, we never go for collection. We always ask botanists to collect that plant for us.
Thank you. Assalamualaikum. I just want to ask you how modern technologies, for example, AI, influence the natural product-based drug discovery.
Good question. There are now traditional subjects, they are linking up with AI, because this is very faster paced research is on, de-replication techniques. De-replication techniques, you do mass of your crude product. I mean, as I said, that one plant, it has millions of compounds in it. Identifying each one of that compound or isolating each one of that compound is extremely difficult. You can say nightmare. But if you do de-replication through LCMS and it is linked with some good database, then it is very fast. Then in LCMS, there is further MS. Yeah, the technique is not only the liquid chromatography with mass spectrometry, and again mass spectrometry. That gives you more idea about millions of compounds, and that MS, and then other techniques, they are also linked with some bioassays. You do LCMS or link LC with HPLC, you do purification, and then in 96 well plates, you do different several assays. And in no time, you can know where the activity is going. In that way, that is all computer modulated. AI is functioning there. So in future, our all subjects, they will phase out if we will not link them with AI. AI is very important tool. And I was most recently, if I have time, can I talk? I have time? Okay. Most recently, I have joined Government Sadiq College Women University as a Vice Chancellor. And I have a plan that I will link all my traditional subjects with AI. I will hire a professional faculty member for every subject. He or she will coordinate with my faculty, for example, botany, zoology, or chemistry, and they will link with AI so that when our graduate they will go to the market, then they are well equipped. I mean, they should not stay behind from any other professional. Thank you.
Assalamualaikum. Thank you so much, ma'am. It was very impressive talk. My question is, when you talk about anti-prolific activity, how do you examine it? Do you apply it on human body or animal body?
Not yet, because I mean, if we Allah Subhanahu wa Taala has made a very good mix of different things. I mean, when we eat moringa oleifera as a vegetable, we eat whole plant, and there is no side effect at all. But when we work on a single compound, it might cause it might cause toxicity. So the experiment we have done so far, it is on rats and rabbit model, not on human beings for the pure compounds. For crude extract, yes, we did it. It is safer to use. It has zero toxicity. Mhm. Thank you.
Okay, now I would like to call upon Professor Dr. Jamil Anwar. Please come on stage and give the sheets to Shazia. Yeah, Professor Dr. Shazia Amjad. And also Professor Dr. Ishaq. Please come on the stage to receive your shield. Professor Dr. Shah Hussain. Now I request Professor Dr. Ishaq Hussain, please give shade to Professor Dr. Jamil Anwar.
Now we will have lunch break till 2 p.m.
fostering a culture of curiosity and inquiry. The department's research efforts are also focused on sustainability and innovation, with a special emphasis on addressing some of the most pressing challenges facing our planet today. The students in the Department of Chemistry are known for their energy, enthusiasm, and active participation in a variety of extracurricular activities. These students are not only dedicated to their academic pursuits but also have a passion for innovation and creativity. The Department of Chemistry's seminars are designed to be highly interactive, fostering an engaging and dynamic environment for participants to share ideas, ask questions, and collaborate with fellow attendees. The Department of Chemistry at the University of Education, Lahore, is a thriving hub of research, sustainability, and innovation, with a dedicated faculty and a passionate student body. The department is emerging as one of the strongest in the university. Fostering a culture of curiosity and inquiry. The department's research efforts are also focused on sustainability and innovation, with a special emphasis on addressing some of the most pressing challenges facing our planet today. The students in the Department of Chemistry are known for their energy, enthusiasm, and active participation in a variety of extracurricular activities. These students are not only dedicated to their academic pursuits but also have a passion for innovation and creativity. The Department of Chemistry's seminars are designed to be highly interactive, fostering an engaging and dynamic environment for participants to share ideas, ask questions, and collaborate with fellow attendees.
یار یہ اس کی وائس آن کر، اس کی یہ ہے نا کور، اس کو یوں ہی نا وہ ان کے سامنے رکھ
session, there will be panel discussion first. Panel is okay. Assalamualaikum and good afternoon to everyone. Let's move to the closing session. Please warmly welcome Vice Chancellor, University of Education, Professor Dr. Asif Anda Chaudhary, along with Co-Vice Chancellor, Director, Division of Science and Technology, Professor Dr. Alam Saeed, and distinguished guests. I warmly welcome our honorable panelists, Professor Dr. Shadia Anjum, Vice Chancellor, the Government Sadiq College, Women University, Bahawalpur, Professor Dr. Atar Farooq, Comsets Lahore Campus, Professor Dr. Nasir Raza Awan, Lund, Dr. Salman Shakur, MD, Renacon Pharmaceutical Limited, and Mr. Kalimuddin Ahmad, CEO, ChemSol Pakistan, for the panel discussion, conclusion, and recommendation. I request our honorable panelists to come on stage and have their seats placed. Chairperson, Department of Chemistry, Professor Dr. Mia Habibur Rahman Mahmood, will moderate the session. Sir, the floor is yours. Please start the panel discussion.
Bismillahirrahmanirrahim. Welcome to all of you, and thank you very much for you to be here. Today we have panel discussion, and we have various esteemed panelists from industries, from universities, and from academia. Let me briefly introduce
our panelists. First is Professor Dr. Atar Farooq Khan. He is a tenured professor of chemistry at ComFet, IRCBM, Lahore. He is CEO of startup Polnet. He did PhD from Australia and postdoc from UK. He is the Presidential International Fellow of Chinese Academy of Science, and his main work is focused on translation of biomaterials for affordable healthcare in Pakistan. Thank you very much, sir. Our next panelist is Professor Dr. Nasir Raza Awan. He is CEO Spinacure and research scientist at LUMS, Pakistan. He is educationist, neurosurgeon, neuroscientist, and an entrepreneur. He left as professor and head of neurosurgery at Sharif Medical and Dental College in 2021 to start innovative and non-surgical treatment of spine, and is director managing the Center of Spinal Cure, and he is also adjunct faculty at LUM. Welcome, sir. So next we have Professor Dr. Shadi Anjum, Vice Chancellor, Government Saudi College, Women University, Bahawalpur. Madam was the Dean of Science at Islamic University of Bahawalpur, and she is a renowned chemist and scientist in the field of natural product chemistry. Welcome, madam. Next is we have Dr. Salman Shaku, MD Ranacon Pharmaceutical Limited. Ranacon was founded for research and development in 1997 and is pioneer to introduce bicarbonate hemodialysis in Pakistan. Welcome, sir. And next we have Kalimuddin Ahmed. He is CEO Kenso Pakistan. He did master in microbiology and biochemistry and also did MBA. He founded Chemsol in 2007 to serve market of fertilizer, water, soil, and construction material. Welcome, sir. So we have diversity of panelists with us. So let us start our discussion, panel discussion. My first question is from Professor Dr. Asad Farooq Khan. I want to ask you, sir, what do you think the role of modern day academics, and what all have you been involved in addition to your teaching and research?
Thank you, Professor Habibur Rahman, especially for inviting me to this forum. I just want to express my thanks to Professor Akif Anwar Chaudhary for inviting me. The question you asked, basically I am a scientist when I joined ISCBM back in 2011. I'm just like a non-scientist and a normal academician who just teaching and research. But the vibrant environment at our center and the main focus of our center is to do things which are more beneficial to our community, especially in Pakistan, and especially the people who cannot afford vibrant environment at our healthcare materials and the main focus of facilities which are available in modern countries. So this joining my center, the main target is to change myself from an academician to more like a person who can talk about the problems which exist in Pakistan and who can create research which is available for every people in Pakistan. Initially, when we were doing we were not able to see it as a product in a market. When you are a student, mostly you are doing the research, which you can think only I am doing it only for the sake of research. But after joining our center and the atmosphere created by Dr. Akif Ahmed Chaudhary, he was heading our center at that time, that we want to do the research and work which is beneficial for everyone. So from starting from there, I need and I mean I have to pass through different steps, especially involves the steps which are other than research. For example, I have to know how to manage finances, how to use opportunities to my different organizations, how I can use my research or my experience that I can develop products which everybody can and more important uh, that how I can convince common people are important for Pakistan. So after that, first time I'm meeting, I to meet a clinician. For example, because we meet back in 2020, and we went to a surgery room or perform surgery and which kind of what we need. Totally change my understanding the material, the research which I'm going to do. So I need to get out of that. I have to visit hospitals. I have to meet with different industries. What is important for them? So being a research scientist and yes, then to so it passed so what I understand that such many things and it is such it has all the resources to it has he has the manpower and the manpower which is with this intellect is very high, especially in Pakistan students are very they observe performance of 15 years. And other than that, I have or I researchers have an unlimited source of funding. We just only have tap on the right one. We started from a very small building. It's a 8,000 square feet building. And now it's coming now. So these past, I learned that can be a CEO, he can be a businessman, and he can to reach this zone. He to access option there to go out of his seat, go out of his stand, and he need to communicate. He should have communication. He need to be a media so manager of himself. For example, he need to maintain his so I think that academician can do many things which can help to society and overall. Thank you.
Thank you very much, Professor Asad Farooq Khan. Any from the audience who want to ask something?
Medicinal. We have to take the opportunities like the student in competence getting and how important to whole Pakistan. So what I need that we need to realize our students and our all the faculty are for example because it can change the whole scenario. For example, in Pakistan, able to develop first Pakistani products, go to first in man clinical trials. So all these happen due to constant push and constant, you have struggle. So what I say that in Pakistan, many opportunities, especially for academicians, there are not so much competition. And if someone tries, it, he can create a very good portfolio for himself as a CEO or as an academician. Assalamu alaikum, sir. Will you please tell us what is the role of academic in the translation sciences? Actually, this is what I'm talking about. The academician in current Pakistani scenario, there are no R&D labs in the industry. So we have to accept this reality. They will confirm that generally, and most of the industry they do not have a R&D. It costs a lot of money. So the only source of R&D industries are in Pakistan are these universities. So for Pakistan, academicians have a major role for R&D for translation research in Pakistan. But we can. There is no need to target a big product or bigger problem. If you went to industries, they have very small problems, and which you can address and we can answer very quickly. Today, I had a meeting with some industrialist. He had a very big plant. He's going to produce a tons of kgs of some materials, but he didn't know how to quantify them and he didn't know how to get a license for this product. So, due to my knowledge in this field, I have guided him, and they are now going to the contractors. Okay, we'll do it, but we to get out. Academicians need it's very when he out, so that he can allow.
So my question is that how can academic institutions support the culture that supports translational research and also that bridges the gap between the basic sciences and the practical applications?
Okay, yeah, that is the part which I passed through from since first day and
I met people जो मेरी wildest imagination से भी ज़्यादा useful थे, productive थे. I could never imagine that there would be an oasis of PhDs sitting, doing research in different disciplines right next to my hospital, and I didn't know about that. हमारा यही अलमिया है. ये अलमिया नहीं है कि हम रिसर्च नहीं कर रहे. हमारा अलमिया ये है कि हम अपनी आइसोलेटेड पॉकेट्स में बंद हैं, एंड वी डू नॉट गेट आउट एंड इंटरैक्ट. सो जब तक हम एक दूसरे से कम्युनिकेट नहीं करेंगे, मैं अगर सिर्फ मेडिकल कॉन्फ्रेंसेस में बैठा रहूंगा, I will never get an opportunity to meet people who are actually creating stuff, who are actually, inventing things. So I have to, if I'm really facing a problem, instead of just making do वो जो जिसे कहते हैं ना frugal innovation, जिसको जुगाड़ कहते हैं, जो हम पाकिस्तानी जिसमें बहुत ज्यादा experts हैं, बजाय उसके करने के we can do things the proper way, because these are the people who know how to develop things. In passing चीजों में बात हुई, जैसे डॉक्टर अत्तर ने बताया, we came to the hospital actually looking for things that we needed. और बातों बातों में जिक्र हुआ कि जी एक हमारे पास मटेरियल है that we purchase which is made in Holland and it's very expensive, और वो कोई 8,000 रुपए का 1 सेंटीमीटर स्क्वायर है. And Dr. Attar and Dr. Akif, they just looked at it and said, well, we think we can make it. And बात casually मैंने की और वो खत्म हो गई. And 2 or 3 months down the road, Dr. Akif and Dr. Attar showed me, Dr. Yar Saab showed me कि जी ये एक material हमने बनाया है. You remember you told us कि इस तरह का problem है, तो ये will this do? And surprisingly, it is superior than the product we were using in the clinics. हम clinical product mesh की form में use करते हैं. The product that they had made was available as a mesh, as a cottonoid material, as a powder, as a liquid. We could spray the liquid and still it would solidify and make that material. ये वो innovations हैं जो interaction से develop होती हैं. So I believe, और यहाँ पे भी किसी ने question किया था डॉक्टर अत्तर से कि हम translational research में किस तरह आगे प्रोग्रेस कर सकते हैं. बेटा, ट्रांसलेशनल रिसर्च का मतलब ही ये है कि आपकी रिसर्च किसी मीनिंगफुल प्रोडक्ट में ट्रांसलेट कर जाए, एंड दैट कैन ओनली हैपन व्हेन यू नो व्हाट इज मीनिंगफुल, व्हेन यू नो व्हाट वी नीड, व्हेन वी नो कि हमारी रिक्वायरमेंट क्या है. यू कैन ओनली डू दैट बाय क्रॉस डिसिप्लिनरी इंटरेक्शन, cross-institutional interaction, by talking to each other, going to their meetings, trying to understand their language. हम लोग सारे अपनी अपनी लिंगो बोल रहे हैं, हमारी languages different हैं, scientific technical terms different हैं. We will never get across each other unless we familiarize ourselves with each other's languages. And जिस तरह डॉक्टर अत्तर ने कहा, for this we need to get out of our comfort zone. अगर हम clinics में बैठे रहेंगे तो we will never be able to develop. हमारी प्रॉब्लम ही ये है कि हम डेवलपमेंट को एसोसिएट करते हैं with some research in the lab जिसके लिए बहुत सारी मिलियंस की फंडिंग चाहिए. ऐसे नहीं, हमें जिस डॉक्टर अत्तर ने अभी बात की, बेसिक चीजों से स्टार्ट करना. We can start with simpler things. और कुछ नहीं तो वही प्रोडक्ट्स जो ऑलरेडी एग्जिस्ट करती हैं मार्केट में, which we purchase at the cost of a lot many dollars, हम उनको लोकली इंडिजिनस मटीरियल से बना सकते हैं. सो ये सारी चीजें मेरे ख्याल में पॉसिबल हैं इंटरडिसिप्लिनरी इंटरेक्शन के लिए, एंड दैट्स द रीजन आई एम हियर, एंड आई एम रियली ग्लैड कि डॉक्टर आकिफ ने मुझे इनवाइट किया था. थैंक यू.
Thank you very much, sir. Any question from the audience, please?
अस्सलाम वालेकुम, थैंक यू सो मच फॉर इनवाइटिंग अस. सर, मेरा ये क्वेश्चन है कि हम लोग यहाँ पे मोर देन 100 ऑफ स्टूडेंट्स बैठे होंगे फ्रॉम डिफरेंट यूनिवर्सिटीज. but we don't have the market oriented research from any one of us कि जो हमें यहाँ पे शो कर सके कि मैं हूँ जो मार्केट ओरिएंटेड रिसर्च कर रहा हूँ या कर रही हूँ या ऐसी प्रोडक्ट मैंने लॉन्च किया जो कि मैं बाद में एंटरप्रेन्योरशिप के लिए यूज कर सकता हूँ या अपना स्टार्टअप भी शुरू कर सकते हैं. We all are like after graduation, most of us are jobless. So, what do you think? What are the drawbacks and flaws in our research area that can be overcome?
Very good question. This is exactly what me and your Vice Chancellor Saab were talking about while we were coming to this venue. कि हम लोग जो साइंस को समझते हैं कि हमने साइंस की पढ़ाई कर ली और हमने अब जाके आगे पढ़ाना है. Academics is one way we can utilize this science. Academics is one way we can actually make use of our knowledge. There are 100 other ways to use that knowledge. और वो जरूरी नहीं है कि अगर आपने केमिस्ट्री में, माइक्रोबायोलॉजी में, बायोकेमिस्ट्री में किसी चीज में आपने किया हुआ है तो वो आप अपने ही फील्ड को लिमिटेड रहो. There are microbiologists who are working on release of energy using bacteria. वो एनर्जी इंडस्ट्री में जा रहे हैं. There are microbiologists, there are chemists who are not just developing drugs and not just developing chemical materials, they are actually going into things like space technology. So ये सारी चीजें पॉसिबल सिर्फ तब है जब हमारा अपना विजन इतना ब्रॉड हो कि हम अपनी स्पेशलिटी को एनविजन कर सकें where we can utilize that. और उसके लिए बार बार मैं एक ही चीज एम्फसाइज करता हूं बेटा, इंटरैक्शन, interdisciplinary interaction. Talk to people. If you don't know how to sell your product and you have come up with a wonderful idea, talk to the MBA friends जो आपके साथ हैं. Talk to the marketing people. Talk to some agency. ये सारा interaction, ये कोई भी चीज in isolation नहीं होती. और दूसरी बात जो अभी मैं सर के साथ बात कर रहा था, हमारी प्रॉब्लम ये भी है कि हम साइंस को सीरियसली लेना शुरू करते हैं मास्टर्स या उसके बियॉन्ड. हम अंडर ग्रेड लेवल पे साइंस को सिर्फ मींस और स्टेप लैडर के तौर पे यूज करते हैं टू गेट इनटू वन फील्ड और अनदर. इंजीनियर बनना है तो हमने प्री इंजीनियरिंग कर ली, डॉक्टर बनना है तो प्री मेडिकल कर ली. हमारी अंडर ग्रेड और प्री ग्रेजुएशन साइंस है वो सिर्फ इन चीजों के लिए है. आई रिमेम्बर आई वांटेड टू बी अ फिजिसिस्ट और मैं गवर्नमेंट कॉलेज में एडमिशन फॉर्म्स लेने गया तो उसने कहा बेटा किस चीज के फॉर्म्स चाहिए, एंड आई सेड जी फिजिक्स के फॉर्म्स दे दें. और ही स्टार्टेड लाफिंग. उसने कहा पुत्र फिजिक्स के फॉर्म्स कोई नहीं होंगे, या इंजीनियरिंग देने या डॉक्टरी देने, बस ही लेना. मैं प्री इंजीनियरिंग के उठा लाया. सो दैट इज व्हाट नीड्स टू चेंज. We need to emphasize the essence and importance of basic science. All my life, I have tried, at the fag end of my career, I'm proud to say कि हमारे कुछ institutions जिनको मैं influence कर सका हूँ, I've done that, to inculcate basic science into the clinical. क्योंकि मैं डॉक्टर हूँ, मैं clinical sciences पढ़ाता हूँ. I've always tried कि basic sciences पे emphasis हो. हम लोग clinicians जो हैं, we forget that we are also scientists. We forget that we are using the knowledge of our scientific knowledge to treat patients. हम लोग सिर्फ technicians बन जाते हैं. ये चीज सीखी, ये symptom देखा तो ये दवाई दे दी. That's not how things go. So practical applications बहुत सारी हैं. We need to go out and look for them. Keep an open mind, जैसे डॉक्टर अत्तर कह रहे थे. And above all, talk to people, talk to friends. Don't limit yourself to your own discipline alone. That's the only way I can see.
Assalamualaikum, sir. Sir, I have a question. How do you facilitate effective collaboration between clinicians and researchers?
बेटा अभी तक तो जितनी कोलैबोरेशंस हो रही हैं वो सिर्फ सेल्फ मोटिवेटेड और पर्सनल बेसिस पे हो रही हैं, क्योंकि हमारे पास ऐसे कोई प्लेटफॉर्म्स नहीं है जहां पे क्लिनिशियंस भी आए, रिसर्चर्स भी आए, एकेडमिक्स भी आए और इंडस्ट्री भी आए. वो जो कोलैबोरेशन है वो सिर्फ बिटवीन एकेडमिक इंस्टीट्यूशंस एंड रिसर्चर्स एंड क्लिनिशियंस नहीं है, उसमें इंडस्ट्री का भी उतना ही रोल है. अगर आप अपनी प्रोडक्ट को कमर्शलाइज नहीं कर सकोगे, इट्स नो यूज. आपने एक पैटेंट ले लिया है, आपने डिस्कवरी कर ली है और वो आपके शेल्फ में पड़ी हुई है उसकी शील्ड, it's not benefiting anybody. So we need to have platforms like this जहां पर different disciplines से लोग आए. نہ صرف آپس میں ڈسکس کریں, وہ ایک دوسرے کے ساتھ لانگر ٹرم انٹریکشن ڈیولپ کریں. اور وہ تبھی ہو سکتا ہے جب ہمارے پاس اس طرح کے پلیٹ فارمز ڈیولپ ہوں. ڈاکٹر عاقف when he was in ComSats IRCBM, وہاں پہ انہوں نے ایک وہ کیا تھا ڈاکٹر تھا جو وہ آپ انڈسٹریل وہ بنا رہے تھے تھوروفیئر, جس میں ایکڈیمکس اور یہ اور ایک ہے اس طرح کے کلبس ہیں. یہ چیزوں کی ضرورت ہے ہمارے پاس. ہمارے پاس ٹیلنٹ کی کمی نہیں ہے. We do not have any dearth of potential. We do not have any dearth of hardworking people. فرق صرف یہ ہے, we take work to be something that we have to do to earn money. That's not how it should be. Work should be your passion, your fascination. اور بجائے ورک کو فیسنیشن میں بنانے کے, I would motivate you all to find what fascinates you and make that your career. In that way, آپ لوگ ساری عمر ایگزاسٹ نہیں ہوگے. You will never be tired, you will never be bored, and وہ ورک ہی آپ کی انٹرٹینمنٹ ہوگا. So platforms چاہیے ہیں. It is the academic institutions like this where we can start at least. یہ جو انکیوبیٹرز ہیں جس طرح کے, وہ انکیوبیٹرز ہمارے پاس ابھی ٹوٹل لاہور میں میرا خیال ہے 2 یا 3 انکیوبیٹرز ہیں. وی نیڈ پلیسز لائک دیٹ جو نئی بزنسز کو, نئی انڈسٹری کو, نئی ریسرچ کو انٹر ڈسپلنری ایکسپوجر دیں. سو دیٹس پروبیبلی دی اونلی وے وی کین لک گو فارورڈ.
Thank you very much, sir. Our next panelist is Professor Dr. Shadi Anjum, Vice Chancellor, Government Sadiq College, Women University, Bawalpur. Madam, my question is, what role do you think can a university management play in facilitating its researchers to reach out to industry and vice versa? Thank you.
Bismillahirrahmanirrahim. Thank you very much, Dr. Akif. I'm really amazed. This is wonderful closing ceremony of this conference, non-traditional, and I'm really enjoying industrial people around, and especially the exposure that our students are getting. It is marvelous. Thank you so much. Yes, like Dr. Akif, he started it and it won't end, sir. Because in my opinion, university management or a vice chancellor, he's a leader, and a leader is not meant to just order in his or her office. Leader should make a pathway and facilitate his or her team members to make their own ways. Of course, leaders should communicate with industrialists, bring them over to the forum, university forum, and they should also present what they are doing in their industries. ان کا کام کیا ہے, وہ کہاں پر ان کو ہرڈلز آ رہی ہیں, کون کون سی پروڈکٹس یا کون کون سی ٹیکنالوجیز دے آر امپورٹنگ. تو ہماری جو یہاں پر ٹیچرز ہیں وہ انہیں ہیلپ کر سکیں گے تبھی جب انڈسٹری کے لوگ آ کر اپنا پرابلم ڈسکس کریں گے. آف کورس بیکاز وی آر ان اے پروسیس ٹو برج اے گیپ بٹوین یونیورسٹی اینڈ انڈسٹری. اور پھر میں یہ سمجھتی ہوں کہ ہمارے اسٹوڈنٹس کا بھی رول ہے کہ وہ they should be bold enough. They should start asking questions. Whatever topic they are studying in their coursework, وہ اپنے ٹیچر سے پوچھیں why we are studying it. اور پھر اپنے مائنڈ میں سوچیں کہ اس کی اپلیکیشنز کہاں ہوں گی. اگر سمجھ نہیں آ رہی تو اپنے ٹیچر سے پوچھیں کہ ہم یہ پڑھ کیوں رہے 1850s کا نالج, ہمیں بتائیں کہ اس کی اپلیکیشن کہاں ہے. تو obviously پھر وہ ٹیچر بھی اسی لحاظ سے پریپیئر ہو کر آئے گا آپ کے کوشچنس کے بعد کہ ایک ہمارا آج کا اسٹوڈنٹ ہی اور شی از سو ویل اویئر کہ وہ ہم سے پوچھ رہا ہے کہ جو ہم 1850 کا کوئی ٹاپک پڑھا رہے ہیں تو اب ہمیں بھی کنٹمپریری جو نالج ہے اس کی طرف ہمیں آنا چاہیے, اور ہمیں بیسڈ آن جو کمیونٹی یا جو انڈسٹری نیڈ ہے اس حساب سے اپنے کریکولا کو ماڈیفائی کر لینا چاہیے. دیکھیں HEC آپ کو کریکولا دیتا ہے ٹیچرس کے لیے, یہ بات HEC आपको करिकुलर देता है, लेकिन इसका मतलब ये नहीं है कि आप इतना पुराना उन्हें पढ़ाएं कि जो अब नॉलेज ऑब्सलीट हो चुका है। आप इंटरनेशनल जो जर्नल्स हैं उनसे इन टच रहें, जो रिसेंट रिसर्च है, जो जो कुछ मॉडिफिकेशंस हो चुकी हैं उसको अपने सिलेबस में इंक्लूड करें। साथ साथ आप स्टूडेंट को भी बताएं कि उन्हें बल्कि इनकरेज करें कि वो आपसे क्वेश्चन पूछ सकें। और ऑब्वियसली फाउंडेशन बहुत जरूरी है। यूनिवर्सिटीज दे आर मेंट फॉर बेसिक रिसर्च, लेकिन बेसिक रिसर्च से फिर फर्दर इनोवेटिव आइडियाज का जनरेट होना ये भी बहुत जरूरी है। तो उसमें एक टीचर का रोल, क्लास में सिर्फ टीचर का रोल इस तरह नहीं हो कि वो आए, लेक्चर डिलीवर करे एंड दैट्स ऑल। मेरा ये ख्याल है कि आर्ग्यूमेंट्स होनी चाहिए, बैक एंड फोर्थ, स्टूडेंट को अलाउ करें, वो भी आर्ग्यू करे, आप भी उनके क्वेश्चन से उनसे क्वेश्चन पूछे ताकि स्टूडेंट का जो एक थॉट प्रोसेस है वो प्रोवोक हो। और फिर आप अपने स्टूडेंट्स को फ्रीक्वेंटली इंडस्ट्री का विजिट कराएं ताकि वो खुद भी जाकर देखें। लेकिन स्टूडेंट का लेवल क्योंकि वो नहीं होता कि वो एक्चुअली ग्रास रूट लेवल पर इंडस्ट्री की जो डिफरेंट प्रॉब्लम्स है उनको समझ पाए। टीचर्स को जाना होगा, वाइस चांसलर को फैसिलिटेट करना होगा अपने टीचर्स को कि वो उनको डिफरेंट इंडस्ट्रीज में फॉर कपल ऑफ मंथ्स भेजें, टाइम टू टाइम वो जाकर रेलिवेंट इंडस्ट्री में जाकर देखें, उनकी वर्किंग प्रोसेस देखें और फिर वहां से वो आइडियाज लेकर आए कि क्या उनको उन्हें किस तरह से हेल्प करना है इंडस्ट्री को। आप डेवलप वर्ल्ड में जाएं, MIT और कैम्ब्रिज और जितनी भी अच्छी अच्छी यूनिवर्सिटीज हैं वहां पर प्रोफेसर जो है वो इंडस्ट्री वाले खुद उनके पास आकर कांटेक्ट करते हैं कि आप हमें ये प्रोडक्ट डेवलप करके दें। उनके पास इतने पैसे होते हैं कि वो उनके अपनी सैलरी से भी कहीं ज्यादा वो कमा रहे होते हैं। तो हमारे यहाँ ये जो गैप है, हम सिर्फ एक ट्रेडिशनल करिकुला पढ़ाकर हम ये समझते हैं कि हमने अपना फर्ज अदा कर दिया। मुझे ऐसा लगता है कि स्टूडेंट्स और टीचर में गैप बढ़ता जा रहा है क्योंकि पता नहीं क्या हम कुछ बिजनेस ओरिएंटेड हो गए हैं। साल में 2 सेमेस्टर करा के अपने स्टूडेंट्स को हम अपने यूनिवर्सिटी की फाइनेंसेस को स्टूडेंट की फी से चलाना चाहते हैं, ये जबकि मॉडल बिल्कुल फेल्ड मॉडल है। हमें अगर हमने ऐसा किया और हम ऐसा करते रहे तो हमारे स्टूडेंट्स में की क्वालिटी जो है वो पुअर से पुअर होती चली जाएगी। आप यकीन जाने ये बहुत ही अनफॉर्चुनेट होता है कि आप साल में 2 दफा इनटेक लेते हैं, स्टूडेंट्स हमसे पढ़ते हैं और यकीन जाने शक्ल भी भूल जाती है कि ये हमारा कभी स्टूडेंट था, नाम तो दूर की बात है। और अगर आप देखिए जो स्टूडेंट होता है ना, अगर आप उसे बाय नेम बुलाते हैं ना क्लास में तो वो जो एक लिंक डेवलप होता है ना वो जिंदगी में कभी नहीं भूलता। मुझे याद है मैंने जब MSc की थी तो मेरे टीचर बोर्ड की तरफ लिखते थे, कोई क्लास में विस्पर होता था तो वो उस विस्पर से स्टूडेंट को बाय फादर नेम भी कहते थे कि फलां स्टूडेंट और फादर नेम ये क्या इश्यू है। तो वो एक जो एसोसिएशन थी वो अभी तक वो बॉन्डिंग कायम है, लेकिन अब वो बॉन्डिंग आहिस्ता आहिस्ता लूज होती चली जा रही है। तो हमें अपना पूरा सिस्टम रिवाइव करना होगा। इसके लिए ऐसा नहीं है कि टॉप से आकर कोई हमें हेल्प करेगा फाइनेंसिस में, ये तो एक एहसास है, ये तो एथिक्स है हर एक के कि वो अगर आपको सैलरी मिल रही है तो आप अपने आप को कैसे डिवोट करें यूनिवर्सिटी के लिए, इंस्टेड कि आप अपने ऑफिस में बैठकर जस्ट एक ट्रेडिशनल वे में आप वो पढ़ाते चले जाएं। आई एम सॉरी अगर कुछ मुझसे कुछ गलत किया कहा गया तो कोई एडमायर हुआ, लेकिन मैं अपने स्टूडेंट से जरूर कहूंगी कि बी ब्रेव एंड आस्क क्वेश्चन। आप क्वेश्चन से जो लर्न करते हैं ना वो लर्निंग कहीं पर नहीं हो सकती। और टीचर्स के लिए इतना है कि वो इंडस्ट्री में जरूर जाया करें और इंडस्ट्री के लिए हमें इस यूनिवर्सिटी में ऐसे प्लेटफॉर्म भी बनाने चाहिए जिसमें लाइक आज तो पूरा टोटल एकेडमिया का था एटमॉस्फेयर लेक्चर से, हमें इंडस्ट्री के लोगों को भी मौका देना चाहिए कि वो लेक्चर्स दें अपनी इंडस्ट्री में जो डिफरेंट इनके प्रोडक्ट्स डेवलप कर रहे हैं उसके मुताबिक कुछ हमें बताएं और फिर ये बताएं कि क्या क्या चीजें इम्पोर्ट हो रही हैं ताकि हमारे जो टीचर्स हैं वो उसको समझें और उनको हेल्प आउट करें। और एक आखिरी बात कह के मैं बंद कर रही हूँ, वो ये कि मैं ये समझती हूँ कि टीचिंग लोड वाकई ज्यादा होता है। एक अगर असिस्टेंट प्रोफेसर को आप 4 कोर्सेज दे देते हैं तो उसके लिए अपना लेक्चर प्रिपेयर करना, लैब में जाना, वो थोड़ा सा डिफिकल्ट हो जाता है। अगर हम पाकिस्तान में ये भी करें कि 2 स्ट्रीम्स हो, एक रिसर्च स्ट्रीम और दूसरा टीचिंग स्ट्रीम, तो इस तरह जो रिसर्च ओरिएंटेड टीचर्स हैं ऑब्वियसली वो ऑफलोड हो जाएंगे और वो प्रोडक्ट डेवलपमेंट की तरफ ज्यादा आ जाएंगे। और सॉरी, एक और बात भी याद आ गई, वो भी मैं कर लूँ, वो ये कि जैसे आज की कॉन्फ्रेंस थी, हम अगली कॉन्फ्रेंस इस तरह से करें, बेशक किसी प्लेटफॉर्म से करें जिसमें हम इंडस्ट्री के लोगों को बुलाएं, वो लेक्चर्स दें अपनी इंडस्ट्री के बारे में, और फिर जो हमारे पोस्टर्स हो या पोस्टर ना हो हमारे, बल्कि प्रोजेक्ट डिस्प्ले टीचर्स करें कि उनकी जो रिसर्च है वो किस तरह से ट्रांसलेट करें और वो अपनी रिसर्च को टीचर अपनी टीम के साथ अपनी रिसर्च को डिस्प्ले करें इंस्टेड के स्टूडेंट उसे करें। थैंक यू।
Thank you very much, ma'am, for your wonderful talk and suggestion. We will certainly put these suggestions in our next conference. So, any question from the audience, please?
Assalamu alaikum, ma'am. Ma'am, as you talked about the topic of the curriculum, so I have a question regarding the increasing mediocrity of the research topics in different universities. So, ma'am, how can a university or an institute balance the basic research and the industrially focused and applied research for students, ma'am?
In chemistry, there is one subject, applied chemistry. But if you see the curricula for applied chemistry, it is so boring for students, they don't like it. बट अगर वही सब्जेक्ट आप जाकर उसे पर्टिकुलर इंडस्ट्री में जाकर हर एक प्रोसेस उसको समझा दोगे तो वो स्टूडेंट के लिए बहुत ही ज्यादा कभी नहीं भूलेगा वो स्टूडेंट। तो मेरा ये ख्याल है कि थोड़ा सा फील्ड बेस हमें निकल के ट्रेडिशनल क्लासरूम से निकल के काम करना चाहिए। इसमें कोई ज्यादा फाइनेंस नहीं चाहिए होगी, जस्ट एक विल चाहिए होगी। वेयर देयर इज अ विल देयर इज अ वे।
अस्सलाम वालेकुम मैम, मेरा आपसे कोई क्वेश्चन नहीं है। मैं आपका थैंक यू करना चाहूंगी, आपने जो बात की वो हम सब स्टूडेंट्स के दिल की बात थी, दिल की आवाज थी। थैंक यू सो मच।
Ma'am, how can universities incentivize? How can universities incentivize researchers to engage with industries?
बेटा स्टूडेंट्स तो डायरेक्टली जाहिर नहीं कर पाएंगे, टीचर्स को ही वो बनना होगा लिंक, और टीचर्स जाएंगे इंडस्ट्री में, वो देखेंगे, फिर वो आपको अपने साथ एंगेज करेंगे। आपका सिर्फ इतना काम है कि जो भी पढ़ें, जो भी टॉपिक पढ़ें, आप अपने टीचर से जरूर पूछें व्हाई आई एम रीडिंग इट, इसका पर्पस क्या है, इसकी एप्लीकेशन क्या है। जो आप रिसर्च कर रहे हैं उसके मुतालिक भी पूछें कि इतने पैसे टैक्स के इस रिसर्च पर लगे हैं, इसका कम्युनिटी को क्या फायदा है। ठीक है, तो टीचर से पूछें क्वेश्चन। जब मैं लेक्चर देती हूँ तो खड़े होकर मैं सबसे पहले अपने स्टूडेंट्स को बताती हूँ कि जो टॉपिक मैं आपको पढ़ा रही हूँ इसकी एप्लीकेशंस कहाँ कहाँ हैं, और मैं उन्हें इंकरेज करती हूँ कि वो मुझसे पूछें। और मुझे बहुत अच्छा लगता है कि मैं आर्ग्यूमेंट के स्टाइल में उन्हें पढ़ाती हूँ। और दो कि मैं काफी अर्से से मैं एडमिनिस्ट्रेशन में हूँ, लेकिन जहां मुझे मौका मिलता है, जो मेरा वर्कलोड होता है, मैं कभी ऐसा नहीं करती कि अपने सीनियर पीएचडी के स्टूडेंट से कहूँ जाओ मेरे बदले पढ़ा दो। इवन कि मैंने खड़े होकर लैब तक करवाई है। मेरे पास एक्टिंग चार्ज भी होता था, वाइस चांसलर का, मैं डीन भी थी, उसके बावजूद भी मैं लैब में खड़े होकर अपने स्टूडेंट्स को काम कराती हूँ।
Thank you, madam. Dr. Salman Shakur, he is MD Renacon Pharmaceutical Limited. Sir, I have a question. Have you ever felt the need to source scientific input into your industrial operation? Are there any linking platforms that can help you to reach out to academia?
And what is the next question?
Are there any linking platforms that can help you to reach out to academia?
Reach out to?
Academia. Thanks for inviting me. I'm grateful. I think very few in Pakistan can emphasize the need for pure R&D without any support from the government or the community, innovation, and then ultimately a positive outcome. I can give my own example. While I was in charge of hemodialysis in Mayo Hospital, Lahore, there were only 2 dialysis centers, LGH and Mayo Hospital. And as you know, that in the developing countries, 90 to 99% of the patients with end-stage kidney failure die due to non-availability and non-affordability of dialysis, because dialysis is an expensive treatment. Worst condition is in Africa. We have visited several countries where more than 99% die due to non-affordability, basically, and non-availability also. So while I was in charge of dialysis in the hospital, I could see the patients in great misery who were on dialysis, few one who were lucky enough to get the treatment. There was a lot of mortality and morbidity. Low blood pressure, nausea, vomiting, weakness, malnourishment, and ultimately death. BP goes down several times during dialysis, and we used to give them normal saline, and the amount of fluid we were taking out was again given to them. Very frequent deaths and misery I could see. Why? What was the reason? The reason was that a very toxic sort of hemodialysis solution manufactured by one company containing 35 millimole of acetate, which is toxic for the liver and for the body, and I cannot go through technical details or clinical details, was being used in that dialysis solution. Now, 35 millimole of sodium acetate goes to the liver and is converted by the liver into bicarbonate, which is a physiological buffer. It was creating disaster. Now, this acetate hemodialysis concentrate was becoming obsolete in Europe, and they had converted to more physiological and natural form of bicarbonate hemodialysis concentrate. Bicarbonate is a body buffer. So I thought, actually, I was always in R&D. Even Professor Khaja Sadiq was our principal and others. All the research papers of all my professors, associate professors, were written by me. All the research was done by me. Then I joined nephrology from gastroenterology. So I thought we should develop this bicarbonate hemodialysis concentrate in Pakistan. There was no internet, and I had to go from one library to other library, and during international conferences, I used to gather the literature. I joined hand with a PhD doctor who came from abroad, and I did the clinical research, and I did the chemical one in chemistry. It was a very complex chemistry. And then ultimately, we developed bicarbonate hemodialysis concentrate, which was in 2 parts. And of acetate, we can replace it by sodium bicarbonate, which was a physiological buffer. You would say, many of you are all chemists, you would say, why did we add sodium bicarbonate initially in the hemodialysis solution? Because if we add sodium bicarbonate in the hemodialysis solution, it will react with calcium chloride and magnesium chloride, and insoluble carbonates of calcium and magnesium will precipitate, and that becomes useless. So some intelligent person thought, why not make it into 2 parts? Part A, acidic, and part B, sodium bicarbonate, separate, no reaction. So these 2 goes to the machines, diluted 35 times. Part A goes to the machine, part B goes to the machine, diluted 35 times with RO water, reverse osmometer, highly purified water. And this ultimate solution, which is known as dialysate, it runs through the dialyzer or filter against a semi-permeable membrane. Blood passes through the on one side of the semi-permeable membrane that was sterilized. This solution was not sterilized because this bacteria could not cross the membrane. Rather, molecules more than 5,000 daltons and protein molecules could not come out of the blood. So this, we developed it. It was a very complex calculation. And if the pH goes above, blood pH is 7.4. If the pH goes above, these salts would precipitate again in the machine. So we had a lot of bottlenecks to the extent that, as you know, passion is required. Passion, perseverance, and a burning desire is required. The successful people give results, the failures gives excuses. So due to perseverance, we ultimately developed it. And then it changed the quality of life of the people altogether within the same price, because the old acetate dialysis solution in one part was more expensive, and our bicarbonate solution in two parts was less expensive, because I kept the price very low. I said, keep it. Previously, only 1% patients were getting bicarbonate hemodialysis concentrate at 5 times the price being imported, but we kept it the price lower than. Now, those patients who were coming on stretchers and wheelchairs were coming driving the motorcycles and cars, and slowly it spread all over Pakistan. So it changed the quality of life of the patients altogether, without any franchise, but through local R&D, for which several times I had to use my credit card to buy the kits and chemicals. So ultimately, I belong to a purely academic family without business. Somebody told me that we should make a factory to make it commercialized. In 1998, we made the Renacon Pharma, and later on, the work on R&D started. Then we produced the solution form. After that, we produced the powder form, pushing Rockwell, USA, who was importing powder to Pakistan and giving to 4 large institutes of Karachi. We pushed Rockwell, USA out of Pakistan by producing our powder form. And later on, with the kind help and expertise of Dr. Mahmood Ahmed, who was our QC in charge, and he was very active in developing all these products. We developed the cartridges, bags, disinfectants, customized RO plants, and still we are now presently I am developing the nutraceuticals, which are not present in Pakistan, which are very specific, low potassium, low sodium, low phosphate, high calcium, and without heavy metals. So this is customized nutraceuticals which are being developed. Several other products are on the offering. So what I wanted to say, that if somebody has got a burning desire and wants to work, now I would like to say one thing important, that in Pakistan there are so many universities, and I have taken for our quality control in charge, deputy quality control in charge. Now I have taken interviews of hundreds of chemists by now, and I've seen. I would like to say with disappointment that many of them, or the majority of them, did not know what they. I would not go into detail what they ought to know. This was bad, number one. Number two, when I look at their research work, it was very typical sort of research work, which was not applied, which had no relation with the industry. And what I would say, that we need to work on into it, that all the research work should be verified by a committee of consultants and experts in the a university, and look into it, that what are the practical implications of this one. Now, I would say that we are talking a lot, but what help industry is getting out of it? Industry does not know about it, that any university can help them. I have a slide, I would like to read it, that in industry academia liaison, through Higher Education Commission, there are professorship tenure tax system basis. Number one, ORIC, 89 offices. QEC in affiliated college, 29 universities in 20. NC, doctoral research in public-private sectors, 49. Business incubation centers, 38. Technical and innovation support centers, 40. Industrial professionals for 78. Academic experts, this data has been taken from the HEC side and other sites, relevant sites. Academics experts, 722. Chamber of Commerce, which has liaison with the universities, and the HEC for research, 9. Experts from government bodies, 33. Experts from non-government organizations, 15. And representatives from different institutions and universities, 301. But what is the outcome? There is no practical outcome because it has been not been done with the passion, with the desire, with a proper strategy to help the industry. Industry does not know practically what universities can do for them. We are suppose now I will give you an example. We are my passion is to cut down the cost of dialysis as much as we can, not only for Pakistan but all the developing countries. Can you say that, do you know that 44% of the world's dialysis, there are 44% of the world dialysis is done only in 30 countries which are developed like USA, Canada, UAE, this Malaysia, Japan. And 56% of the world's dialysis is done in 180 countries and territories which are poor and developing. This is very bad because 90 to 99% patients die. So we need to, my aim, my passion is to provide the best quality to cost ratio in the world. And in that connection, I have visited several African countries and I have offered them that we provide you dialysis at very low cost. I will give you simple one example because time is less. Recently, one of my professor, professor pediatrics from Congo was in Australia. He told me that I should go to Congo and help the government in getting cheap dialysis. So he arranged meetings. I went to Congo with a population of 110 million, and there was I met the minister, deputy minister, signed an MOU with DG Health, and according to the populations, they should have 200,000 patients of dialysis if everybody gets dialysis. But you will be astonished to know Pakistan has got 35,000 patients on dialysis. Still better, they had only 550 patients on dialysis. Pakistan has got price per dialysis session is $16 to $17. And what was the price of per dialysis session three times per week in order to stay alive was $250. Why? Because only the filthy rich were getting dialysis. There is no middle class. In the sub-Saharan African 42 countries, there is only the richest, the most corrupt, and the poorest. So I offered them dialysis at $25 to $30, giving them each and every expense. And for the past 1 year, I have sent them the whole business proposal for 150 machines, 5 dialysis centers. No response because I did a mistake. What was the mistake? I should have told them that $25 are for the dialysis and 25 for you. Then you should have done. So this is the condition.
Thank you, sir. Thank you very much, sir.
Thank you very much. So this was at the end of it, I would say that number one, two things, that a proper strategic planning, through HEC and the universities, a liaison between the universities and the industry should be developed. Industry does not know what you can do. You are doing a lot, I would say. If you can do this project, why not that one? But you are not targeted. And number two, industry does not know. They need to know. Number one.
This is important.
Thank you very much, sir.
Thank you.
Any question, please, from the audience?
Sir, we are thankful to you to all of you for being here in this conference. Sir, I just have a question. What platforms or network do you use to connect with the academic researchers? What platforms or network do you use to connect with the academic researchers?
What I would say that so far I would say if it is done properly, HEC is the best platform, and HEC should make liaison with the chambers of commerce and industry, hold seminars, and tell them through their newsletters that this university is doing this and this and this project. And they should also say that HEC should be the best media to gain collaboration between the industry and academia. But I think I've told you what HEC shows in its website, but what is the practical outcome? I don't see any practical outcome into 10.
Okay, thank you.
Okay. Thank you very much. Let's move to the next panelist. We have Kalimuddin Ahmed, CEO CAMSOL Pakistan. Sir, I have the same question for you. I will repeat. Have you ever felt the need to source scientific input into your industrial operation? Are there any linking platform that can help you to reach out to academia, sir?
Bismillahirrahmanirrahim. Thank you very much for inviting me here. I am probably the most uneducated person present in this panel. Can you hear me? सबक फिर फड़ सदाकत का, अदालत का, शजाअत का, लिया जाएगा तुझसे काम दुनिया की इमामत का. और बहुत कड़ी जिम्मेदारी डाल दी है इन लोगों ने मेरे नाजुक कंधों पर. 4 लोगों के बोलने के बाद मेरी बारी है. डॉक्टर साहब, आपका क्वेश्चन मुझे बिल्कुल इंडस्ट्री को ये नीड फील होती है कि एकेडमिया के साथ कोई राब्ता किया जाए, और लेकिन कोई ऐसा लिंकिंग प्लेटफॉर्म अवेलेबल नहीं है. मैं आपको 2 चीजें नरेट करूंगा अपनी. मेरा तजुर्बा तकरीबन इस इंडस्ट्री का, केमिकल इंडस्ट्री में मुझे तकरीबन 40 साल हो गए, और मैं फिर आपके साथ वैसे तो 150 स्टोरीज हैं, सिर्फ 2 आपके साथ शेयर करता हूं. हमारे एक दोस्त है जो पोस्ट डॉक्टोरल रिसर्च कर रहे थे अयूब रिसर्च सेंटर में, और उन्होंने एक सिट्रिक एसिड बनाया. मैं तारुफ में उन्होंने बताया कि जी मैं सीईओ हूँ अपनी कंपनी का, हूँ मैं सीईओ, बाय डिफॉल्ट आई एम सेल्समैन, मैं सेल्समैन हूँ. तो उन्होंने सिट्रिक एसिड बनाया, और ऐसे ही किसी खाने के ऊपर मुझसे मुलाकात हुई. उन्होंने कहा मैंने सिट्रिक एसिड बनाया है. मैंने कहा शायद ये ऐसे ही बात कर रहे हैं. मैंने कहा मुझे दीजिएगा थोड़ा सा. मैं वो लेकर कराची गया जोड़िया बाजार में, और जो सबसे बड़ा सिट्रिक एसिड वो प्रोडक्ट है जिसके 200 कंटेनर पाकिस्तान में इंपोर्ट होते हैं, और वो उन्होंने मोलासेस से बनाया था. मैंने वो सिट्रिक एसिड उनको दिखाया. वो ट्रेडर था, वो पढ़ा लिखा नहीं था. उसने वो एक दाना उठाया, उसका चक्का, कहेगा कि ये बेल्जियम का है. तो मैंने कहा आपको क्या लग रहा है? कहेंगे ये बेल्जियम का है. मैंने कहा तो आप कितने का ले लेंगे? तो उन्होंने कहा था उसकी 16 रुपए कॉस्ट है. तो कहेंगे मैं $2.5 से ज्यादा आपको इसकी प्राइस नहीं दूंगा. तो जितने भी कंटेनर पड़े हुए हैं मुझे आप दे दें. मैं वापस आया, उनसे मैंने बात की. मैंने कहा कि मुझे ये सिट्रिक एसिड की फॉर्मुलेशन आप दे दें. कहेंगे यार देखो मैं हो गया हूँ बुढ़ा, और मैंने अपनी जिंदगी में कोई गलत काम नहीं किया. तो मैं ये चाहता हूँ कि गवर्नमेंट के जरिए इसको आप परचेज करें. इत्तेफाक ये है कि उस जमाने में मेरे टीचर हैं
جو وفاقی وزیر ہوا کرتے تھے HEC کے ڈاکٹر عطاء الرحمان، میں ان کے پاس گیا اور ان سے کہا کہ سر یہ میں نے فارمولیشن پرچیز کرنی ہے، تو گورنمنٹ آف پاکستان کو کتنے پیسے چاہیے ہوں گے؟ تو کہیں گے 10,000 روپے میں ہم دے دیتے ہیں فارمولیشن. تو میں نے کہا دے دیں. انہوں نے وہ اپلیکیشن کے اوپر سائن کر دیا اور کہیں گے منسٹری آف کامرس چلے جاؤ. تو 2 سال کی محنت مشقت اور منسٹریوں کے اندر سر مارنے کے بعد ایک دن اپروول مل گیا کہ جی آپ فارمولیشن پرچیز کر سکتے ہیں. اس عرصے میں وہ جو ڈاکٹر صاحب تھے وہ ریٹائر ہو چکے تھے. جیسے ہی وہ اپروول ملا تو ہم نے اس کو سوچا کہ یہ تو بہت اچھی بات ہے. تیسرے دن انہوں نے کہا کہ ایک اور لیٹر آ گیا کہ یہ اپروول کینسل ہو گئے. انہوں نے کہا کہ جی گورنمنٹ آف پاکستان سٹرک ایسڈ خود بیچے گی. تو ٹھیک ہے وہ بیچے، لیکن یہ سن 2002 کی بات ہے اور آج سن 2024 ہے. کوئی سٹرک ایسڈ پاکستان میں نہیں بکتا. وہ بیچارہ پتہ نہیں کس فائلوں کی زینت ہے. اسی عرصے میں ڈاکٹر عطاء الرحمان کے پاس گیا اور میں نے کہا کہ ڈاکٹر صاحب مجھے ایک کام کریں کہ مجھے گنے کی پروڈکشن دے دیں پاکستان میں پورے میں، اور پاکستان مجھ سے واپس لے لیں 5 سال میں، جس میں کوئی آدمی غریب نہیں ہوگا. جو لوگ کیمسٹری کے ہیں ان کو تو غمزدہ ہونا ہی نہیں چاہیے. یہ کبھی ہماری بیٹی نے سوال کیا تھا کہ جی ہم تو جاب لیس ہیں. جاب لیس ہونے کی کیا ضرورت ہے آپ لوگوں کو؟ آپ نے بل گیٹس کی اسٹوری نہیں پڑھی؟ آپ دوسرے لوگوں کی اسٹوری نہیں پڑھتے؟ یہ میرے ساتھ بیٹھے ہوئے ڈاکٹر صاحب، آپ کبھی ان کی اسٹوری سنیں کہ کس طرح فرام ریکس ٹو ریچز بندہ بنتا ہے. اور کیمسٹری والوں کو غمزدہ نہیں ہونا چاہیے بھائی، بالکل. اور اگر اس میں کوئی مسئلہ ہو تو مجھ سے آگے بعد میں بات کر لیں. میں پرانے زمانے کا ٹیچر ہوں، مجھے تو مارنے کی عادت ہے. بیسک مسئلہ یہ کہ کسی بھی انڈسٹری، ملک کی جو اکانومی ہے وہ 2 چیزوں کے اوپر کھڑی ہوتی ہے. ایک بیسک انجینئرنگ انڈسٹری اور ایک بیسک کیمیکل انڈسٹری. آپ کیمسٹری میں آ گئے، آپ نے ماسٹرز کر لیا، لیکن آپ کو یہ پتہ نہیں ہے کہ بیسک کیمیکل انڈسٹری پاکستان میں ہے یا نہیں ہے. ایک اور صاحب نے سوال کیا تھا کہ جی ہمیں کیسے پتہ چلے گا کہ جی ہم کیا کریں گے. میں اسٹوڈینٹس اور ٹیچرز دونوں سے کہتا ہوں پلیز ٹرینڈز دیکھیں. یہ گوگل ہماری فیسیلیٹیٹ کرتا ہے. آپ دنیا میں دیکھیں گے ٹرینڈز کیا چل رہے ہیں، مٹیریلز کے اوپر کیا ٹرینڈ چل رہا ہے آپ کے پاس. اور یہ ساری ہمارے پاس را مٹیریل بہت سارے پلاسٹکس کے اویلیبل نہیں ہیں، لیکن ہائیڈروجن تو اویلیبل ہے. ہائیڈروجن ایز اے فیول آپ کیوں نہیں کام کرتے؟ یہ کس نے روکا ہے آپ کو؟ کبھی کسی نے آپ کو یہ پروجیکٹ نہیں دیا کہ ہائیڈروجن ایز اے فیول کام کرے اس کے اوپر؟ یہ سب کے لیے ایک اٹ از جسٹ اے پوائنٹ ٹو پونڈر کہ جی آپ سوچیں کہ ہمارے پاس کیا چیز نہیں ہے. صرف بیسک کیمیکل انڈسٹری نہیں ہے. پاکستان میں ہم بہت ساری چیزیں کرتے ہیں اور بہت سارے لوگوں نے کہا کہ یہ چیز ہونی چاہیے، انڈسٹری اور اکیڈمیا کو ہونا چاہیے. میں بتاؤں نہیں ہو سکتا، نہیں ہو سکتا. یہ آئی ایم سوری. کیوں نہیں ہو سکتا؟ اس لیے نہیں ہو سکتا کہ ہماری گورنمنٹ نے کوئی فریم ورک نہیں دیا. HEC کی سائٹ کے اوپر چلے جائیں، وہ آپ کو ضرور بتائے گی کہ کون کون سے ڈاکٹرز کس کس چیز کے اوپر ریسرچ کر رہے ہیں. لیکن دیکھیں جو ڈاکٹر ریسرچ کر رہے ہیں اس کا آبجیکٹو کیا ہے؟ میں اکثر لوگوں سے ملتا ہوں، میری بہت سارے لوگوں سے دوستیاں ہیں، وہ بات کر رہے ہوتے ہیں BPS کے اوپر کہ یار ہمارا BPS 17 ہو گیا، 18 ہو گیا، 19 ہو گیا، 20 ہو گیا، اور کیا اس کے ساتھ بینیفٹس اٹیچ ہے. انڈسٹریلسٹ کیا بات کرتا ہے؟ انڈسٹریلسٹ کا آبجیکٹو الگ ہے. وہ کہتا ہے کہ پروفٹس کتنے. جب تک ان دونوں کو آپ کہیں کامن چیز کے اوپر نہیں لے کر آئیں گے، اور دونوں کو ڈاکٹر صاحب نے جیسے بالکل صحیح کہا کہ وہ ایک پیشن ہونا چاہیے، پرسیویرنس ہونی چاہیے، اور برننگ ڈیزائر کے بغیر یہ ممکن نہیں ہے. اور یہ چند ہی لوگ کر سکتے ہیں. I have traveled a lot in this world. میں آپ کو ایک بات بتا دوں بچوں کو. Pakistanis are the most enterprising people in the world. Rest assured, most enterprising. چاہے وہ آپ اکیڈیمکس کی دنیا میں چلے جائیں یا آپ کرائم کی دنیا میں چلے جائیں, آپ کو دونوں کو جینیس دیتے. تو یہ کوئی ہلکی بات نہیں ہے. ہم اپنے ہیروز کو پتہ نہیں کیوں بھول جاتے ہیں, اور وہ ایسے ہی نہیں بنا دیا کسی نے آ کے یہاں پر نیوکلیئر بم بنا کے چلا گیا. وہ اس کے پاس چیزیں اویلیبل نہیں تھیں, اس نے اسی انوائرمنٹ میں کام کیا. آپ لوگ کیوں گھبرا رہے ہیں بھائی؟ آپ لوگوں کو کوئی پریشان ہونے کی ضرورت نہیں ہے. جب ہم بم بنا سکتے ہیں تو ساری چیز. میں ایران گیا تو ایران کا چیمبر آف کامرس کا پریزیڈنٹ مجھ سے حقارت والے انداز میں پوچھ رہا تھا کہ پاکستانی کیا بناتے ہو تم لوگ؟ اور وہاں پہ سیرینس, لیبنیز اور جورڈانینز بیٹھے ہوئے تھے. تو میں نے کرٹسی میں خاموش رہا. پھر اس نے دوسری دفعہ سوال کیا کہ یہ پاکستانی کیا بناتے ہیں؟ جب اس نے تیسری دفعہ سوال کیا تو میں نے کہا جی ہم تو سوئی سے لے کر ایٹم بم تک بناتے ہیں, آپ بتائیں آپ کو کیا چیز چاہیے. سر پوائنٹ یہ ہے کہ ہم اپنے وسائل کو ٹھیک طرح سے استعمال کریں, اور یہ جب تک ایک فریم ورک نہیں ہوگا انڈسٹری کے لیے. میں آپ کو چھوٹی سی مثال دیتا ہوں. یہ سٹرک ایسڈ بنایا ہے, یہ سٹرک ایسڈ کی فارمولیشن جو 16 روپے کا بنایا اور $2.5 کا وہ بیچ رہے ہیں, وہ خرید لے گا. آپ کو کیا اندازہ ہے کہ اس میں کتنا فرق ہے؟ تو یہ اس میں کس کو فائدہ ہونا چاہیے؟ یہ ایک دفعہ فائدہ ہونا چاہیے یا مستقل؟ یہ سوال ہے جو جن کے جواب کون دے گا. یہ جواب میں آپ کو بتاؤں میں اور آپ نہیں دے سکتے. یہ جواب دیتی ہے حکومت, اور وہ بھی ایک فریم ورک بناتی ہے. سر پرسنٹیجز, میں ابھی کسی سے بات کر رہا تھا, میں نے کہا مجھے بیسک را مٹیریل چاہیے. آپ یہ میں آپ کو بتاتا ہوں, میں ٹیکسٹائل میں کام کرتا ہوں. یہاں پہ کسی نے کہا کہ جی R&D نہیں ہوتی ہمارے یونٹس میں. پاکستان میں جو سب سے بڑا ایکسپورٹر ہے, انٹرلوپ, نشاط, سفائر, لکی گروپ, یہ لوگ اپنی R&D کے بغیر نہیں چلتے. لیدر میں آپ شفی گروپ کو اگر آپ دیکھ لیں تو جو یعنی 70 بلین کی ایکسپورٹ ہماری ٹیکسٹائل کی ہے, اور تقریباً 30 بلین کی لیدر کی ہے. وہ لوگ R&D کے بغیر نہیں چلتے.
Sorry, sir, we are getting late.
سوری,
We are getting late. I request you to wind up, please.
ٹھیک ہے. تو آئیڈیا یہ کہ یہ انڈسٹری اور اکیڈیمیا کا جب تک پلیٹ فارم گورنمنٹ نہیں بنائے گی یہ کام نہیں ہو سکے گا, کیونکہ اس میں پیسے انوالو ہے, ٹائم لائنز انوالو ہے. کیونکہ ریسرچ والے لوگ ریسرچ کرنا چاہتے ہیں, بزنس والے لوگوں کو جب پیسے دے رہے ہوتے ہیں تو ان کو فوری طور پر پروفٹ چاہیے ہوتا ہے. تھینک یو ویری مچ.
Thank you very much, sir. Any question from the audience, please?
السلام علیکم. سر میرا وقت سے ٹاپک سے ریلیٹڈ نہیں ہے, لیکن تھوڑا سا کہ میں نے دو آلموسٹ تقریباً یہاں پہ 400 لوگ بیٹھے ہوئے ہیں ہال میں, تو اس میں 395 لوگ لوکل ہیں اور 5 فورنر بیٹھے ہیں. تو ہم 5 فورنر کے لیے اپنا موڈ آف لینگویج ہی چینج کر دیتے ہیں. میں انگلش لینگویج کی اہمیت کا انگلش لینگویج کی اہمیت کا اہمیت نو میم میرا کوشچن سنیے گا کہ میں انگلش لینگویج کی اہمیت کا انکاری بالکل بھی نہیں ہے, لیکن میرا کوشچن یہ ہے کہ اگر آپ لوگ کسی فارن کنٹری میں جائیں, فار ایگزامپل چائنا میں جائیں یا کسی یورپین کنٹری میں جائیں, تو آپ لوگوں کے لیے کیا وہ لوگ اپنا ٹوٹلی موڈ چینج کر دیں گے اور اردو میں کر دیں گے وہ اپنی اسپیچز کو؟
Any other question, please, if relevant to the topic? Okay.
Thanks to all of you. मैंने ना सबकी बातें ना बड़े गौर से सुनी है. What I feel, I mean, if I put myself, let's say, in the backstairs with the student and considering myself as a man,
Be silent, please.
So
be silent, please.
To be very honest, for me, being a learner, मैं तो सबके comments को combine करूँ, it's very confusing to be very honest. Academics का point of view is a different, industry का point of view is a different. Industry is talking a lot about, even academics is talking about the government, HSC government. कुछ चीजें की हैं मैं क्योंकि आपने ज्यादा गवर्नमेंट पे स्ट्रेस किया, मैं एक छोटा सा कमेंट करता हूँ कि 4-5 साल से गवर्नमेंट आपको में लाना चाह रही है टैक्स के. यू पीपल आर नॉट, आप नहीं आ रहे उनके करीब. आई मीन यू मीन दी जो ट्रेडर इंडस्ट्री के सारे लोग हैं वो नहीं आना चाह रहे. दे डोंट वांट टू हेल्प गवर्नमेंट टू डू. आई मीन गवर्नमेंट के पास इकोनॉमिक स्ट्रेंथ है सो दैट दे स्टार्ट थिंकिंग अबाउट अदर थिंग्स. और की बात हुई, आई टोटली एग्री कि 10-15 साल से और इज देयर एंड वो बिल्कुल बात आपकी ठीक है कि औरिक ने, मैं उसको ब्लेम नहीं करता, बट सम हो औरिक वाजंट ट्रेन्ड इनफ टू परफॉर्म समथिंग. तो confusing, I mean, we want to, I mean, again, with respect to a learner, we want to clear that confusion. What exactly is lacking? हमें अगर एक problem का
sorry, we got your point. Thank you very much. With this, I will request worthy Vice Chancellor, Professor Dr. Akif Chaudhary, to please share the concluding remarks.
जी, Bismillahirrahmanirrahim. Honorable faculty members, guests from Pakistan and beyond, dear students, and our honorable panel members. Assalamu alaikum. How are you? Very good. First of all, I'm interested with two responsibilities in this interaction. One is to collate all the positive recommendations and the questions and the queries of our younger minds and everybody put together. And the second one is also to congratulate you all and also the organizers for the successful closure of Tric 2024. So Tric 2024 was not our first event. And it has spread all over 2 days. You've had people, you've had talks, you've got poster sessions, and you've talked a lot about science. You've brought people together from other countries. You brought people together from other cities of Pakistan. And you have given us a launching pad of enough core science where we can today talk about that how science has benefited society or not. So first of all, I think we must put our hands together for the students who are here, for the faculty who is here, for everyone who has joined us from the industry who is here, and also the organizers. And also to our sponsors, incidentally, which includes the Higher Education Commission as well, which has allowed us to hold this panel discussion. So a big thank you. So I think this sets the tempo. University of Education, mashallah, there are 3 numbers, 975. We've got 9 campuses. We are present in 7 cities, and we've got 5 very strong divisions, right? We were ranked between 1,200 and 1,400 universities in a year. We made an appearance 2 years ago, and the team here has done exceptionally well now to move into the 1,000 to the 1,200 category. And our 5 divisions, they include science and technology, very vibrant ecosystem. And most of the team here belongs to that division, honorable sirs and madams. And then we've got arts and social sciences. We've got education. We've got Islam studies and Oriental languages. And we've got one more. We've got business and administration sciences. Now, in this ecosystem, we want to create connectivity. But without launching pad, without this core R&D, without our faculty members, it's not possible to talk about translation of research. There's a lot of publication bashing that goes on,
But I think it's very important to understand that if you are a high profile company working anywhere in the world or in Pakistan, you're looking for contracted research. You're looking for an established portfolio of R&D. Is R&D mere what we call reverse engineering to launch a product? Is it actually truly innovative? And are you actually talking about patenting your R&D? You're talking about patent commercialization and so on and so forth. So within R&D as well, we need to refer to both areas. Summing up, I think there was a very good question by Dr. Saab over here who mentioned that when we talk about R&D and dividends and whether we are CEOs of our own companies, but how will the nation or the university, how can they benefit from efforts into this commercialization? That is very true. There are certain frameworks which we can do as public sector universities. There is licensing of technology. There's licensing dividends that go into the university ecosystem. So when we talk about the knowledge economy, where knowledge translates into economical dividends, you as a university have a huge role to play. You as a student have a huge role to play. You as a faculty member have got a huge role to play, because what you're talking about is about sustaining an economy. So first, moving from the taker status to a sustainable status to a giver status. There was another question or a comment about that we are functioning indeed in islands of excellence and we speak different languages. That was very true. There's a need for cohesion. There's a need frameworks. We can talk about the absence of frameworks, but we cannot deny the existence of existing launching pads. We already have existing launching pads available, because this is a huge debate. We can talk about the push strategy. We can talk about the pull strategy at the same place. There's the concept of self-aggregation for students of science. There is nothing stopping us from making choices, for deciding to like each other, from deciding to work, and deciding to become those frameworks that we say those frameworks are absent. What is stopping us from becoming those frameworks? So we can ask these bolder questions. There was a student who mentioned, we are not sure whether the R&D that we are doing is market-oriented or not. The way forward is that how do you select a science project? There are either projects available to you through a mechanism, through the deans, through the professors, through the supervisors. There's another option as well. You can also design a project. And this is what the connectivity and knowledge and homework and following trends that the panel members or honorable were talking about, is that you can also bring a lot to the table. When we were working in R&D, we realized when we were people of science in scientific labs, we had students coming in from clinical backgrounds. Professor Nasir Raza Awan was heading a telementoring group of second-year MBBS students at King Edward Medical University. That's where the team of scientists realized that we may traditionally identify ourselves as teachers and them as students. But as far as our clinical knowledge went, we were the students and they were the teachers. So it is how we approach knowledge flow. So I'm really glad for all the members who are here today. There was also a talk about role of leaders and vice chancellors and university administration in facilitating our people in towards translational science. And Honorable Madam, who has joined us, really grateful. It's very true, because I think this is a new movement in Pakistan where there's a term where people say positions of power. But I think there's another word, a term we can use to view these positions, where we call them positions of responsibility. They are positions of high responsibility for deliver. One of the other intentions that we have at University of Education is to use this term very easily. And the term is, I don't know. Why is everybody so morbidly afraid of using this term? I don't know. And I think this is where the acceptance of knowledge gap lies, because if you don't recognize that knowledge gap, you will never go work towards a solution as well. I think we must all agree that today we were talking about us speaking different languages, and we have people from different backgrounds in this hall. And I think on its own for everybody to be sitting here together in this event. I think this is a success on its own. We hope, we hope that instead of pointing fingers, because when we point one finger, we have at least three fingers pointing to ourselves. We have to look forward. If we speak different languages, let's accept this gap. And let's talk about that there's an absence of technology translators. The technology translator may be from a banking mechanism, maybe from a financial system, they may be from scientific background or different backgrounds. Let's create more technology translators in our ecosystem. Training doesn't end. Training doesn't end when you do a PhD. It doesn't end even when you become a professor. So, but as a university, we have to talk about professional development. When we talk about students, we have to talk about professional development. I met an architect back in Turkey, and he asked us, okay, which year are you working in? The country for the young student asking about languages was Turkey, where I took the education in English. And they offered that education in English. And there's a saying in Turkish, they say, big deal, big insan. They say one language, one human being. More the languages, more the facets of human face. And they asked us, which year are you in, young man? And I said, fourth year. And I asked him, what are you doing? He was a leading architect for the big company known as Imar. The students might know the name. People might know the name, Imar. And he said, well, I'm in my 56th year of education. So that changed the perspective because learning never changes. So let's hope for a tomorrow where it is easy to use the words, I don't know. Let's talk about bridging our gaps. And there's a success case that I would show. We can bring a lot of meaning to a lot of what happens. Because we know of scientists from different backgrounds. You know, you're familiar with the Higher Education Commission Technology Development Fund. You're familiar with the Pakistan Science Foundation triple helix science models, right? They all require a letter of support from the industry. Now we've got to be honest with ourselves. Is it our mamu or Falu or my friend's father who has given us that letter? Or is it actually truly an industrial person whom we are invested in to develop our contact? So platforms may already be there, but it's just that we need to probably change our filters and goggles and see what more we can do. So there are people who in Pakistan have launched products in the market. They are changing lives of people to develop hemostats and wound dressings from this very HEC Technology Development Fund. They've crossed those barriers of what a non-disclosure agreement is. What comes after science? You do an R&D, MS thesis hai, PhD thesis hai, patent karna is probably about 30% easier than the very complicated publications that you people write. And then the reviewers send you very strong reviewers and sometimes nasty comments. And then you defend your those nasty comments, you defend your concepts. And so patenting is probably about 3 times easier than that. But what do you do when you have a patent? We have to talk about commercialization. We have to talk about exploitation. And that's where the honorable members from the business community come in. What they're talking about, they've got a nubs pe unka haath hai. They understand कि एक country में कितनी चीज आती है, कितनी चीज जाती है, उसकी क्या need है. They are good people in exploiting opportunities and avenues. At the end of the day, I think this has been a fantastic experience. My hats off to the organizers for agreeing with me to have a slight change in the closing ceremony. A big hat to the overall Division of Science and Technology led by the Pro-Vice Chancellor. A big hat off to the Chair of Chemistry. A big hat to all the organizing committee sitting behind me, sitting everywhere. And a big hat off for all the panel discussion members for coming here today and pulling our brain in multiple directions. So we look forward to seeing you again, inshallah. Pakistan Zindabad.
Thank you very much, sir. Now it's time for souvenir distribution. I will request for the Vice Chancellor, Professor Dr. Akif Anwar Chaudhary, to please come on stage, and Professor Dr. Muhammad Alam Saeed, Pro Vice Chancellor, University of Education, to please come on stage and distribute souvenirs. Professor Atal Farooq Khan, our panelist. He is also my class, Professor Atal Farooq Khan. Professor Nasir Azawan. Professor Dr. Shadi Anjum, Vice Chancellor, Government Science College, German University, Bahawalpur. Dr. Salman Shakur, CEO Renacon Pharmaceutical Limited. Mr. Kalimuddin Ahmed, CEO Cancol Pakistan. I would request Chaudhry Naveed Ahmed, who had sponsored our conference, Salwa Group of Industry. For certificate of appreciation to the organizer, I would request the chemistry department faculty members to please come one by one and get their certificate. So please hurry up. Dr. Muhammad Aslam. Dr. Muhammad Aslam was the secretary of this conference and he has managed this event wonderfully. Dr. Amna Asghar. Dr. Misbah Shah. Dr. Misbah Shah. Dr. Muhammad Adnan Asad. Ms. Sadia Bashir. Dr. Sayyid Salman Shafkat. Dr. Mahmood Ahmed. Dr. Biswanath. And Dr. Muhammad Ahmed. Poster. And we have Best Poster Presentation Award goes to Mahmood Fatma from UET. And now it's turn for the students who organized this event. Ms. Memuna Ishaq. Memuna. Next is Asif Hanif Chaudhary. Next is Muhammad Ali Javed. Mr. Suhaib Warid. Thank you very much, sir. And this is the end of our conference. Thank you very much for your participation and to be here.